Okay.
All right.
Okay.
Hello,
So,
gentlemen.
welcome to India.
I wish I could be there, really.
Yes.
As I told you, I was in India really a lifetime ago. You know, like it was in '77. Can you imagine?
Oh, yes.
And then I never had an occasion to come there. So let's use this virtual trip at least.
Yes.
To feel to be there.
So can you try once sharing your screen?
Absolutely. Okay, let's see what happens. Okay, share. Share. This is it. This is it. This is it.
Okay.
See?
Yes.
Do you see it?
Yes.
Yes.
Okay. So let's stop it.
You can project it if you want, or
okay. Well, if you want.
No, let me do mine. Then we'll switch over to yours. One second.
Yeah.
Let me share mine.
Okay. How do you? Because I don't see my when I share the screen, I don't see this screen that you show right now with the images of the participants and the shared screen.
Maybe you have a dual monitor. Do you have two monitors?
No. Just a little laptop.
So if you don't go on full screen mode, then you'll see this one.
Okay. No, just a second. I can do Windows.
Yeah, you can try that.
Windows here. Share. Okay, perfecto. So if I do this, and if I do this, this is takes the whole screen away.
Oh, okay.
Yeah, but now let's see what happens. Yeah, this you see my screen, right?
Yes.
Okay, but I don't see it.
Okay, 1 second, sir. Can you go to view here? View, go to view in this
Hold
dialog.
on a second. Let me try another experiment.
Okay.
So if I put it full screen here and then I go back here, and now I see everything, but I don't. But I need to go to this one to the. Okay, that's all right. Yes, please tell me what.
Yeah, it works now. Whatever you did, if you are able to see yourself, that is fine.
Well, yeah, I'm not able to see myself because I cannot move forward with the presentation if I do that.
Okay, can we go back? You come out of slideshow mode.
Yes. Okay. Let me see.
You can try going to view at the top, view tab.
Allora, view tab.
Home, insert, draw,
there
view.
it is. Okay, view.
Within that, no, it's not updating for us. Have you gone to view tab? Click on view, please.
I click on view. Yeah.
No, for some reason, we don't see the view tab. We still see slideshow tab.
Okay. Okay. Let's see. Where is it? No, this is
Home, insert, draw, design, transition, view.
You see, I never use Chrome, so that's why it's an additional problem. So view on Chrome, you mean?
No. PowerPoint or
PowerPoint.
whatever.
Okay.
You have
PowerPoint.
there.
It is view.
View.
Okay.
Go to the view. Click on view.
Yes, I did.
No, we don't see it yet.
Well, because I didn't share the screen, I think. No, you should be able to see it.
We are still click on the view. Yeah, we can see draw. Then.
Yeah, but I click up there and you don't see it.
We see your mouse moving. Come down, please. Transition, animation, slideshow.
Oh, okay.
Next of it.
Yes, this one. Okay.
Yes,
right.
yes.
Okay. Sorry.
There is a reading view in that 5th item.
Okay.
Yeah, please click that.
Yes, I did.
Nothing changed. Did you click on it?
Yeah, I think I did. That's
some strange issue. Can you please stop sharing and again?
okay. There it is. Yeah, but don't worry. I don't mind not seeing myself. You know, it's not a very pleasant view, so I can live very well without it. So it's a reading view. Let's see. If I do a share at this point, what tells me? Windows, but then I need to have it. Yeah, I need to have it on the same screen because I have multiple screen active. So let's do the following. Let's get this one back here. This stop show. And we got this one. And we got this one here. Okay, now we are back to where we started.
It's not shared with us yet.
No, I haven't shared. Let
Okay.
me share it right now. Share Windows. This one here. Share. Be able to see.
Okay, it's loading.
The thing is that when I go in full mode, I have perhaps here. What do you see?
Not yet. I mean, we just see the
No.
PowerPoint.
Yes, it doesn't. This reading mode doesn't work for me because it.
Okay.
So I need to put it here. Now you should be able to see it.
Yes.
Okay. So if I move it to a different window, like that. Okay, so I can switch from one screen to the other, and one screen I have the view of you, and the other I have the presentation. So I guess this is the best way to go.
Okay, so you can just try to change and see whether it's changing.
Yes. Okay.
Okay.
Very good.
So we'll start in another 2 minutes. So how is the vaccination scene? Are you vaccinated?
Oh yeah. How is the situation in India? We hear horrible stories here in Europe about the situation there.
But now it has improved. So I got my second shot of vaccine yesterday.
Okay. So let's hope it's under control.
It is under control. It went up very sharply and it came down equally sharply.
Okay. That's well, vaccination does miracle. Also here, yesterday we had like 22 people, 20 deaths, something like that, respect to 800 of a couple of months ago. So it was a very sharp decline. But still, it's like 9/11. Now it will leave permanent attention and damages or whatever. Our life will be changed, unfortunately.
Yes. Okay, I think we can slowly start, right?
Yeah, whenever you want.
Yeah, I'll just introduce you. So good afternoon, everybody. After lunch, I hope you had a good lunch, and we start the afternoon session. So it's my great privilege and honor to be introducing Professor Paolo Fiorini from the University of Verona. So Professor Fiorini obtained his bachelor's degree from the University of Paoda, his MS in electrical engineering from University of California at Irvine, a PhD from University of California at Los Angeles. From 1985 to 2000, he was with NASA Jet Propulsion Labs at Caltech, where he worked on automation and teleoperation systems for space applications. 2001, he returned to Italy, and he set up the Altair Robotics Lab. And 2009, he has also started his surgical robotics company. Professor Fiorini is a fellow of IEEE and is currently a professor in the Department of Computer Science at the University of Verona. He also holds joint appointments at Caltech in the US and Obuda University. So Professor Fiorini, welcome, and it's a great honor for us that you have agreed to speak to us. So I would request you to please take the stage.
Thank you very much, Professor Dutta. Thank you for the introduction. Thank you for inviting me, and thank you everybody for attending this talk. Is everything okay? Do you see everything as planned?
Yes.
Okay, very good. So let me get started. As you see, the title is a little bit strange: Dreams in Medical and Surgical Robotics. Intelligence and affordability. And in fact, I will be talking about these long-term plans that I have of addressing one problem which is emerging these days about medical robotics. And the problem is that it's following. I call it a medical robotics divide. The physical interaction is given by robots, and robots are showing that this physical interaction is necessary. In Europe, we have this buzzword that is the digitization and be able to have all digitized process. But in medicine, if you don't go to the physical interaction with people, then digitization stops at a certain point. Stops with prescriptions, stops with medical records, but it doesn't go any further. Furthermore, the current epidemic situation has shown that if we have means to separate people from the medical personnel, we could improve the safety and the health of all of them. And although robotics is not a magic bullet for everything, it has the advantage of improving the average quality. So, great surgeons do perform very, very well, no matter what, everywhere. But other situation, robotics can raise the quality. So therefore, robots seems to have a place in medicine, in the surgery. However, they're very expensive. Their use is limited to very, very few institutions. Even in the so-called rich world, Western rich world, not everybody, very, very few institutions can afford these devices. So are we, separating the preventing people for taking advantage of this technology just because of cost? Furthermore, the design of the robot is addressing only the very expensive procedures, because of course there is a higher return of the economy. There are funds that is received from the national health system, depends heavily on the type of intervention that is carried out. So really, we have to propose a new design and market paradigm and a new approach to medical robotics. Of course, this is the dream. This is a commercial activity, is driven by economics. The cost of developing a medical robot is incredible. And so, of course, people want to take advantage of the situation. But on the other hand, there are other possibilities. And when I say new approach, I think that we have to look at procedures that have the highest impact, not the highest economic return. Somehow we need to limit the profit of medical robotic devices. The profit that these companies make, and Intuitive Surgical is an example. Intuitive Surgical, just to give you a term of comparison, is valued much more than Volkswagen, which is the largest car producer in Europe. And the Volkswagen produces several million cars a year, and Intuitive produces several thousand robots a year. So there is something that is wrong here. How we can do? Well, we can save money, use economic components, and of course we have to provide software compensation, so to be able to compensate the lower performance of the economic components. So basically get savings from other fields, from mass products. And of course, robots, medical robots, rehabilitation, surgical, are not mass products. We can never have the economy of scale that we have in other products. And we have to add software feature instead of expensive hardware. So this talk will be about this feature, in particular about autonomy, also advanced control, a little bit about teleoperation. I heard a couple of talks this morning addressing the issue of force feedback. I will address it very briefly later on. And also simulation, which is a way to simplify the procedures and learn how to do them. I will specifically about these two projects, ARS and PROST. ARS they're both funded by the European Research Council, which is the equivalent of NSF in Europe, and funds the ARS project is theoretically based, so it's really pure science-based, and try to address the issues related to autonomy, in particular in robotic surgery, which is a field very strange with peculiar difficulties. And then PROST is called a proof of concept. So how the concept developed in ours can be applied to a commercial product. And here we are trying to develop, as I said earlier, something that is addressing a very large impact procedure, prostate biopsy, that address in Europe. There are more than 1.5 million procedures carried out every year. And the flip side of the situation is that since it's a low-cost procedure, is done, I don't say carelessly, but with somehow fast and try to reduce the cost. And the result is that there is still 30% of diagnostic error. So a robotic device could significantly improve this in the context of an autonomous robot. So we'll go through all these points to try to emphasize the fact that we should really be consistent to the fact that medicine should be a value for everybody. And of course, people have to make a profit out of it, but not at the expense of the impact on the healthcare system. So let me go briefly to this definition. Your autonomy. There was also another plenary talk yesterday about autonomy. There will be another plenary talk. So it's a topic of a certain interest currently. And this classification was developed by Professor Guangzhong Yang a couple of years ago, together with a number of other colleagues, and reproduces the classification that is done in the field of automotive for the robotic surgery. And in particular, level 0 is now we have mostly teleoperation. All the systems have teleoperation features. And autonomy is limited to do very invisible function like redundancy resolution, tremor suppression, things like that. Then 1 and 2 are the levels that, excuse me, I think are mostly at our reach. So basically, level 1 provides some assistance, both cognitive and physical assistance to the surgeon, and level 2 provides task level assistance. So let's say you're doing a suture, and the knot is a repetitive task, and this can be done autonomously. So within a tight control, with the tight control of a surgeon. Then conditional autonomy refers to the fact that sections of entire procedures can be given to the autonomy of the robots after the procedure has been evaluated and approved by a physician. And then, of course, higher autonomy, full automation is the future steps. And the work is mostly addressing these two levels. How do we go from autonomy to task assistant, and now we go from task assistant to task autonomy? Why is that? Well, because they are shared situations, shared in the sense that both the robot and the human are acting at the same time, share information, share cooperation. Instead, task autonomy is a more traded kind of control. So during one time interval, the surgeon is in charge, and another time interval, the robot is in charge. Although they are, the basic levels, they are, in my opinion, the most critical, because they require that the robot in his own autonomy reaches a good level of understanding of the situation and know what's going on, is able to understand what the surgeon is doing to provide advice, to provide support, and so forth. So critical to this part is the situation awareness of the intervention. And so you see here some of the key challenges that we have to face. How do we represent the knowledge of the intervention? And you'll see a number of aspects. How do we do the planning? How do we do situation awareness? The anatomical environment is very, very difficult. So, it's not easy to address it. How do we do control? How do you demonstrate? And then some other issues, the importance of simulation, the importance of evaluation, and then of course haptics. The last talk of the morning here was about haptics, so I will return on the topic because it's an open question in the field of surgical robotics, whether haptics is useful or not. So where are we developing these technologies? Well, we were lucky enough that Intuitive Surgical has donated a number of these surgical robots to research laboratories worldwide. There are about 40 of these laboratories, these robots given to laboratories, and each one of us is developing some specific aspect. This is the first generation of the Intuitive Da Vinci surgical robot, and when they go out of warranty and out of being useful for clinical application, they are donated to the different laboratories. And in particularly, the task that we are addressing is this one here. It's very simple. It's still not a real surgical task, but is the training task that all surgeons have to go through to prove their dexterity before they address more difficult tasks. It basically is to pick up rings of different colors, put them on pegs, and share it between the two manipulators. You see, this is the three-arm version of the Da Vinci robot. You see here, with this yellow band, one arm. This is the green arm, the other one, and in the middle there is an arm with the camera, the endoscopic camera, which is here, and we enhance the camera with an RGB camera to have also depth perception. The reason for that is that the stereo vision through the endoscope is very limited because the inter-camera distance on the endoscope is very, very limited, and it doesn't allow us to have a good depth of field. So the key problem that we want to address is knowledge representation. Knowledge is present everywhere. There are a number of books on surgical procedures, on robotic surgical procedures. Surgeons are very willing to provide advice, and then we can simply learn from task or get the data. So basically, we addressing these two parts. These two, of course, textbooks and interviews come together. Task duplication, we call it as transfer knowledge, and then learn knowledge from bottom-up data. It must be said that differently, contrary all other types of automation, especially industrial automation, surgical automation is very welcome by the surgical community. Surgeons, as you are very well aware, are always overworked. Always, they have incredible schedules and they work like crazy. So any type of support we can provide them is greatly welcome. And so we are lucky that we are developing this technology towards customers that are eager to accept and to use them. So we have no Ludism kind situation in this field. How do we separate this knowledge acquisition? I define it in these two different fields, the top-down and the bottom-up knowledge acquisition. Top-down, well, we have a priori knowledge. We have textbooks, and so we can extract the procedures from text, but then we need also some sort of background knowledge. Textbooks, of course, don't tell you that if you punch a vessel, there will be bleeding. This is sort of known thing that all surgeons know, but the computer and the robot, of course, do not know that. So we have to use something that's called ontologies that represent all the relation and the consequences of actions and the instruments, and they give all the definitions. And then the critical part is define the logical rules that allow the procedure to move forward, to proceed through all the different states. So this is a tricky part, and you will see how we address it. And then there is the bottom-up part. I know big data are a big fashion, big fad also in surgery. Unfortunately, data are really not available because the surgical robots are very closed machines, and there is a debate going on between the manufacturer and the hospital on whom is the real owner of the data. But fortunately, with the research robot that we have in the laboratory, which is called Da Vinci Research Kit, we can acquire the data and get some technology developed. And the other point is how do we move within, we use the framework of hybrid systems. So hybrid system has modes, the discrete states of the procedure, and then within every discrete state there is a continuous state which is the motion that pick up a needle, pick up a thread, and so forth. And we solve that problem using the formalism of discrete dynamic motion primitives, and you will see what it is. So how do we extract procedure from text? Well, in the text we have two types of sentences: procedural sentences and declarative sentences. And of course, we are interested in procedural knowledge. But of course, this is a brand new area of research. There are no known ways to address surgical knowledge from a textbook. So we had to, first of all, define what is a procedure. And basically a procedure is a workflow. But the critical part is this one here. How do we go through the different steps, defining the precondition, postconditions, and so forth? And you will see the examples that we have. These are some of the procedures the method that we're using to extract these sentences from the text. And it's very interesting because, of course, we are doing this in collaboration with surgeons, and this is stimulating our difficulties in defining the right way and understanding the right words. Is stimulating them to think about writing their textbooks in surgery in a different way, in a way that is more suitable for machine understanding. We had to define data sets. Define data set means that we have to go through the painful and excruciating long procedure of labeling every sentence, every part of a sentence as a procedural declarative, so that we can use machine learning methods. And here is some of the results. And we just signed an agreement with a robotic textbook on robotics procedures to use the whole text to do this machine learning process. This is FastText is a tool developed by Facebook, and we have been comparing it to classical recurrent neural networks. Ontology is the background knowledge that we need to have, and there are, as you see here, two different ontologies. One is called FMA ontology that describes the anatomy of the body, and the other OntoSPM that describes the tools of surgery. And so one important thing is to connect the procedure with the ontology. Think that you are developing your robotic procedure, and of course you develop the nominal procedure. Textbooks usually give you the best case, and then there are section about exceptions and different cases. And if you find an exception, then you have to replan your task, and you have to use this ontology to figure out what are the alternative solutions. For instance, you may not happen to have the right instrument at that moment, so what are the equivalent instruments? Then you go to the ontology. And here the difficult part, how do we represent the transition from one state, one action to the other? And the important thing is that we have to represent these rules in a way that is understandable to people. You are certainly aware of this new field of research. It's called explainable AI. And we address this problem using logic rule representation. It's not the fastest, it's not the latest, it's not this neural network, which on the other hand are not understandable. The results don't allow you to understand how the network reached a certain result. And instead, using logical rules, as you see, is very clear what happens. And then these rules are also easily to be adapted to a changing environment. And in fact, these are the points that the advantage of this approach, which is called this ASP, answer set programming, because we define the variables in statics, which are the description of the environment, and then there are these variables that are called fluents, and they're the ones that define on which the situation awareness is defined. and so is constantly updated by the sensing system, and that allows to provide robots with the situation awareness and allows the evolution of the evolution of the task. ASP has some other advantage. It is non-monotonic reason. It deals with incomplete knowledge, and this is a way to compute a plan. So basically, we find the sequence of rules that satisfy all the constraints, and there are these satisfiability checking tools that allow to solve the problem and to get the sequence. It's called exactly the answer set. So all the logical rules that represent the evolution of a task. Just to give you a brief example, now these are the actions that we want to do in this simple training task: grasping, moving, extracting, very simple things. And their representation in logical form is this. Again, it's not perhaps easily understandable to a surgeon, but it can be translated in a natural language in a very, very simple way. These are some of the results. You will see a brief video later on. This approach allows us to deal with failure condition, with unexpected situation like occupied pegs, so we cannot do the expected, we have to replan the task, and then allows to have multiple actuators, multiple agents in a parallel execution. And so this is very interesting. So we're able to do this training task in a fully autonomous way, and we are trying to compare the performance of a human with the performance of the robot. The rationale behind that is that if we want to certify, this is a very, very long-term objective. We want to certify a robot for clinical practice. The robot will be reasoning, and so it will be practicing medicine. And so he has to go through the same procedure, certification procedure of a human surgeon. So it's a very long way, but we will work on that. We can improve this knowledge, and here you see an example. Of course, in robotics, you cannot use real robots because by the time we generate enough data, the robot will be broken. So basically, we use simulations, and we are able to use this inductive logic programming to refine the set of rules and to learn new rules, providing examples of execution or proper executions. The other way is to use the data. Data allows us to identify the phases of the intervention, and especially to model the surgical gesture. So basically, we have these two components. We have discrete components are the modes of a hybrid system, and the continuous component, the continuous trajectory within each mode, which is the movement of a surgical arm, the grasping of a needle, the insertion of a needle. So the single actions, the form that in a chain of actions form the surgical procedure. This is the standard model of a hybrid automaton, which we are using for this mathematical modeling. And you see the problem is very difficult. Here we're working on this problem with our colleagues at Caltech, Professor Joel Burdick and his students, to try to find ways that even in the, we call a relaxed identification problem, where we know how many states there are in this model, try to find where each state stops and what are the proper sequence. And of course, this is a problem because if we assume that the number of states is fixed, then if there is a change or an unexpected situation, unexpected state, then it's not clear how we modify the model and include this unexpected state, unexpected discrete state in an unexpected mode into the mathematical model. The continuous part instead is being solved quite well. We use this dynamic motion primitives or movement primitives, depending, and this basically can be learned. All these parameters you see here, the capital letters, can be learned even with a single repetition. In reality, we use a small number of repetition to have some sort of average resulting, and we can compute both the trajectory, a Cartesian trajectory, and the rotation trajectory using this unit quaternion. And this is how we learn. Again, you saw the simulation. We can do the learning with industrial robots. So basically, we learn the motion with a easily accessible device. And here is the most tricky part, how to learn from the real surgical data. We are working on this part right now. The good thing of this approach is that on the left you see the learn trajectory with the industrial robot, and on the right you see the executed trajectory with the surgical robot, and you see the shape is more or less the same. This qualitatively the same, but the scale is completely different. And this is a characteristic of this DMP, or the addition that we made of this DMP formalism, to be able to be invariant to the scale and invariant to rotations and so forth. This is just an example of how the motion is learned and how is executed on the surgical robot. Situation awareness is basically the clock, the tick, the events that make the procedure advance. So basically we are considering motion. We have no contact yet, because we still the issue of measuring contact forces is very difficult in a surgical environment. But we need to have a very good, very calibrated eyes and measurement to know where all the different elements are, and to be able to put everything in the same reference frame. So we made a new way to calibrate the robot, and we actually improved by almost 4 times the standard calibration methods. And with all these results, we made this very simple architecture to do to execute this task planning. You see, they're all basically task planning. There is the human monitoring, because we need all this to allow a person to interact. And here is where teleoperation comes into play. And here is just an example of this execution. And you see, this is the task, and this is the planning that comes out. So it's very simple. Here the peg was dropped, but the system recognized that the peg was dropped, because a fluent that was grabbed the peg was instead of being a positive answer, was a negative. And so the system was able to replan, and here replan the parallel execution, which is a little bit new, that not many laboratories in the world are able to do that. And the other part that I want to address is simulation, because we use simulation as some sort of background thinking or unconscious thinking of our autonomous robot, but also with a very practical use. We developed some models of deformation. You are certainly aware that using finite element methods is not very practical in a real-time application, because they are very lengthy, but they are very precise. And so again, also in this way, we have this learning from simulation that allows us to provide enough realistic data to train. In this case, we use neural network, because they are very fast, and it can be used in real time as a virtual sensor that allows us to carry out the procedure. Here simulation is useful also to verify the plans, but once the plan is executed, of course, there will be differences between what we expected at the beginning and what is the reality. And so we have this feedback loop from the execution, that we go to modify the plan, and also to modify the parameters of the biomechanical parameters of our simulation, so that we have this continuous learning and updating of the system. Where did we apply? Well, a simple thing, lifting a piece of plastic or a simulator of anatomical part, and identifying what are the fixation points of that anatomical part. This is a tricky part, a tricky knowledge, because it's not it's different from every individual. It's not visible from the exterior, and so it has to be. And the surgeon learns by trying and error, by lifting different parts and see where it gives and where it doesn't give. And we follow the same approach. And by simulating and creating a number of simulations, we were able to train a neural network to identify that. And here you can see a little bit of an example how we lifted. The task is to lift this yellow part, which is supposed a simulation of fat, to expose a kidney tumor which is underneath. And so there was a little bit of learning, quite a little bit of learning done in simulation. You see that the robot is performing rather poorly, and then eventually it is able to carry out the task autonomously and without further training. And by the way, we also did this with an ex vivo model, so basically a kidney extracted from a pig, and the results were also very robust and applicable to situation also different from the one that which was learned initially. Here, very briefly, to assess the quality of the performance of the surgical robot, we have to develop new metrics, because the current metrics, which are based on Cartesian space, do not capture all the different characteristics of the motion. So basically, we develop new metrics in joint space. Of course, here is convenient because we have access to the values of the joint variables, because we have this Da Vinci Research Kit. Normally, you can only access the Cartesian, so basically the external parameters. But if we use these internal variables of the robot, we are able to have a much better classification and much better identification of the performance and of the characteristic of the robot. So you see, we get from 75%, which is the classification that is normally done simply with Cartesian space, evaluation of performance, dexterity, economy of motion. There are a number of parameters here. You see here some of them that we used. And if we use the metrics both in Cartesian and joint spaces, we reach 86%, which is still not 100%, but is a good result in terms of classification. And here, okay, just to move a little bit further, why do we want to use force feedback? If you remember at the beginning, I said that it is very important to be able to separate the patient from the medical personnel. In this epidemic situation, it was clear, especially in Italy, we had the first part of the epidemics, a number of physicians and nurses that died because of contamination and infection. And so teleoperation would have been a great success. But teleoperation is normally done without force feedback. Current robotics devices do not have force feedback for a number of reasons. From a control point of view, you may generate instability, but from a practical point of view, there are no sensors that can be put on a surgical robot. Sensors cannot be sterilized. No, instruments have to be sterilized. They go 120 degrees centigrade. And so right now, there are no ways to get this sensor to survive a sterilization. And robotic instruments are very expensive. And so, they cannot be thrown out after a single use. And unfortunately, nobody has been developing disposable surgical instruments. So this is another area that we should address. But here we do this work because there is an ongoing debate between surgeons who use the Da Vinci robot in clinical practice and have been trained and learn how to use it very well. And they claim that force feedback is not useful, and surgeons who never use the Da Vinci Research, Da Vinci robot, and they say that they will really, they found that the force feedback is really helpful, especially in the training phase. And we would like to see whether this force feedback is a confusing element or is a favorable element also for surgeons who have been trained in this standard approach. Of course, if you are trained in a certain way and you get this force feedback that moves your hands and creates strange perception, could clearly be a disruptive, confusing element. So we will carry out a lot of experiments with surgeon to understand whether this is true or not. And here, to get the stability, we use this passivity approach with the energy tanks, which is a normal approach now, probably the most popular, but in collaboration with colleagues at University of Modena and Reggio, Professor Christian Secchi, we use an optimization. Here there is an optimization to be able to optimize the flow of energy between one part and the other, the master and the slave, so that there is no abrupt instability or abrupt flow of energy when there is a delay or when there is a interruption of communication. And in the case of rigid environment, force feedback is essential. We proved it when I was at JPL 20-something years ago, because of course you have no visual feedback that allows you to estimate the deformation of, so therefore the forces apply to a deformable object. A rigid object doesn't deform, and so there is no visual feedback that you can use. Instead, in the case of deformable environment, you have force feedback. You have, visual feedback, and so you have these two competing feedbacks that the brain has to sort out. Here we apply this energy tank approach with optimization, using first an industrial robot, the KUKA lightweight robot with a soft environment, being able to maintain stability in contact in spite of time delay, communication time delay. And then we apply the same concept to the Da Vinci Research Kit, DVRK. And we try to use the standard peg in all. You see, this is still preliminary data. You see the robot is still a little bit shaky. And because we think that there are trade-offs between the stiffness of the environment and the level of force feedback. Probably if the environment is completely stiff, we need to provide a lot of force feedback. If the environment is soft, then perhaps the visual feedback will be sufficient to execute the task without uncertainty, and of course without risk of instability. So basically, we will be addressing these two issues with our experiments. And then to complete this talk, I would like to present the result of the other project that has been funding me for the last year or so, on this robot for prostate biopsy. So biopsy is usually done in two ways, either transanal biopsy or transperineal biopsy. And the trend is going to transperineal biopsy because it allows less risk of infections and is somehow more controlled. However, what is done right now is that you see here, this is the biopsy needle, and to be able to cover, unfortunately, the cancer, prostate cancer, is not like a liver cancer, which is a very specific area, some sort of cystic shape. The liver cancer is like, the prostate cancer is like breast cancer, so basically it's spread through all the tissue. And so it's not sufficient to sample the areas that are most prominent, that have some sort of pathological representation, but you have to cover the whole gland with sampling. And so the procedure is usually carried out in the operating room with full anesthesia, and the number 16, 24 holes that are done through a template to sample all the positions, the 4 quadrants on the prostate. Now the trend is to try to avoid this expensive, because you need anesthesia and so forth, and to have only 1 or 2 entry points in the skin to be able to sample the whole set, all the points of the prostate. But of course, it's very tricky to do it by hand, and therefore we decided to have this very, very simple robotic support to guide the robot to the right position, especially to provide the robot with the proper orientation to reach the target. So we provide, and here we say that we have a level 1 of autonomy, because we provide cognitive support in the task identification. So basically we make We've used the diagnostic images, the magnetic resonance images with the real-time ultrasound images. We map the targets, and using, again, also very fast neural network, we are able to provide the physician with a number of candidate target points for the sampling. Once the physician approves the target points, these are transferred to coordinates for the robot, and the robot is moved to the right position. You see a very, very simple design. This prototype cost like 800 euros to be developed. We carried out experiments in the laboratory. We carried out experiments in cadaveric laboratory, and now we are in the process of certifying the new version of this robot for clinical trial. But again, this is an example of a very high impact procedure with a very low cost device. The cost will probably be in the in a few tens of thousands of euros. So basically the cost of an echographer machine that almost every urologist has, and will not be having a big impact on the healthcare, but it will have on the cost of the healthcare, but will have a big impact on the diagnostic capability. In fact, the experiment that we carried out, we had several tests with cadaveric models, and we reached the accuracy that is able to sample the smallest lesions that are visible on the magnetic resonance. So basically, the lesions that are considered dangerous in the prostate cancer are those above 5 millimeters. Below 5 millimeters are sort of thing that has to be monitored, but they do not require an immediate intervention. And so we are able to guarantee below 2 millimeters accuracy, so that we can sample very closely to the target points and ensure whether identify the lesion, whether it's a benign or a malign cancer. And we provide the real-time visualization. We do automatic segmentation. As I said, all intelligence, if you allow me the term, features that make a very economic and very accessible device with a very high performance. And we went through all this validation with tests and with cadaveric tests. So basically, to conclude, so we have a few minutes for question and answers. Intelligent machines are being used in medicine, and probably they should be used even more, not because our physicians need their support, but because they are overworked, and often they are tired, and often they overlook things. And so having a device that can provide guidance or suggestion or warn about increasing of fatigue. Another colleague of ours, Professor Marco Zenati at Harvard, is monitoring the level of stress during open heart surgery, and when the level reaches it's above a certain level, basically it means that the surgeon has no room to react to emergencies. So being able to know what is your level of stress and how much spare energy you have is fundamental to be able to carry out a procedure with some margin of safety. Autonomy and attention to cost are useful tools. Cost is not a parameter that is included in our design. You never can write a paper because you make an economic project or you save money or something, but we made some proposal to the European Union just to address the development of advanced algorithms to compensate the use of economic products. So we'll see how this will be evaluated. And then autonomy is fashionable, is getting very useful. We can reach autonomy up to level 3. Right now, I didn't mention, but we are addressing, of course, with plastic phantoms, a complete intervention. We are having a bunch of surgeons coming over, executing on a phantom. We are collecting data. We are trying to model how they do it. So hopefully by the end of the project, we'll be able to have, as we did with the peg and ring task, a full partial nephrectomy executed autonomously by the robot, and that would be a great result. But of course, we cannot use this. Certification and the regulatory barriers for machines that learn and change themselves and then adapt are still very far behind, and so we have to overcome this legal lag between the research and the application. And with this, I end my talk, and this is part of my team, and thank you very much for your attention.
Thank you, Professor Fiorini, for this very educative and futuristic talk. I'm surprised that in such a short time you have covered so many topics. Yes, there were many, and each one is a very, very important topic. I think you can talk on something like force feedback for hours.
Yeah, keep in mind that every topic is one or two PhD students working. So the speed was the trade-off with the lack of in-depth analysis.
Yes, it was very interesting. Thank you very much. So if there are questions, we'd like to take questions. Yeah, so there is a question there. Is the context of affordability in testing materials can naturally available things like fruit, vegetable, and plants be used as textures?
Let's see. I didn't understand. Okay, question answer here. Let's see. In testing materials, there are
I think what he wants to ask is, can the robot also be used for testing?
For testing materials.
Yeah, like fruits, vegetables, plants.
Of course. Right now, at least in Europe, we see industrial robot being sold to very reasonable price, at least for the European standards. So now we can buy a cooperative robot, the latest generation, the Franca Emica, for about 19,000 euros. And this raises a very interesting point because in Europe we have a significant problem of aging artisans and so forth, who they are not able to find younger that they want to take over the profession. Putting a cooperative robot with the ability to learn inside of an artisan and getting trained to repeat certain tasks, especially fatiguing tasks, could be a very useful thing. So in a sense, testing materials, doing other tasks that are not surgical, not industrial, but very, very small things, shoemakers or furniture makers. There are a number of industries, especially in my area of Italy, disappear or are disappearing because there are no youngs who are interested in doing that. So this autonomy and learning could be a very useful tool to overcome these problems.
Yeah, there is another question there.
Uh-huh.
How much the accuracy and repeatability of the end effector in the peg hole insertion task?
Here it depends on our system, or the combination of our sensing system and the accuracy of the robot. Keep in mind that the robot we're using is a rather old device. It's about 20 years old, and so its accuracy is millimeter to millimeters, and more or less the repeatability is the same, which is more or less the same accuracy of our sensing system. So we have these 2-3 millimeters of accuracy altogether. So it's okay for the peg and ring, and you saw that the pegs are much smaller than the rings, and it was pretty easy to insert them. It would be a little bit more tricky when we do, for instance, suturing and try to insert the needle, and even grasping the needle is a very difficult problem. The features of the needle. The needle is something that is like 3-5 millimeters long for less than 1 millimeter thick, and it's very difficult to identify with regular cameras and things like that. So sensing, as I said at the beginning, sensing is a very critical problem, and probably is the main stumbling block of moving forward.
Okay, so there is another one. So Professor, you put across hybrid model details of discrete systems. Can you underpin on how you identified states and applied that in the robots that you worked on?
Okay, this is a very difficult question. So basically, we have two approaches. One is the one that is developed at Caltech, and that I don't know very much about the probability distributions and analysis, probabilistic analysis of the data. And in our case, basically continuity of motion. So we assume that each discrete state, it's called the modes, are characterized by continuous motion of the robot, represented by this DMP approach. So basically, we try to figure out when there is a discontinuity in the motion of the robot, or the motion given by the surgeon using the robot, and determine at that point the separation between modes. So basically, we solve the problem in the hypothesis that the motion is represented by this DMP. So again, it's not a completely general solution, but at least it gives us a way.
Okay, I think we have time for a few more questions. Next question is, what may be the major concept to be considered while development of an ontology for a prosthetic hand? Specifically, if the task is object recognition using haptic features only.
Let's see. I don't see this. Oh, ontology. Okay. What is the major concern? For a prosthetic hand. This is very interesting because you could, well, first of all, you assume that you have a system that is able to recognize your environment. So the prosthetic hand must have some local intelligence, and of course you have the human that is able to approach a device. He wants to grasp an apple rather than a bottle, and so probably the system has to recognize and do some pre-shaping, adapting his grasping shape to the. So I don't know whether the user of the prosthetic hand can send commands, sensory commands, probably not. So depending on the sensor, on the sensory feedback of the prosthetic hand, the hand has to adapt itself to to shape itself to the proper pre-shaping to grasp the object. However, I don't think that ontologies are rather slow to approach, so I don't think they are very appropriate for this very specific and very real-time task. We are using ontologies when we need to do some replanning, so it take a second, 2 or 3 to try to figure out what is the background of a replane of a task, and then use it. So it's sort of semi-real time in this sense.
Okay, so we have one last question. In the context of machine learning approach, are you using some special sensors in the task area for data collection? How expensive are these new sensors?
Okay, so first of all, when we do machine learning, we use a simulation. Unless we are Google, you cannot do learning with real robots. I'm sure you are aware of the experiment that was done by Google to learn object grasping, and basically after a few months of
His voice is not heard.
Yeah, I think that voice has got cut. You can send him a
He is still seen in the list.
But his picture is frozen, right?
Yes, picture is frozen. Maybe we can just. Okay.
So we can just wait 2 minutes. He might reconnect.
Yeah.
No, he's still there. Well, now he's gone.
Yeah, he's joining back.
Okay, so my apology. The network disappeared for a moment, but
Yes, I think some network issue, yes.
it happens. So I was saying that machine learning with real physical object is impossible. You break them. So the simulation is a good way to go, and then in that case you really don't need a very expensive sensor. On the other hand, the sensor that we're using are the regular RGB camera, the Intel Xsense, so it's really not very expensive, and we are experimenting with putting strain gauges on the robots just to follow this philosophy of low cost and high performance, if we're able to do it.
Okay. Thank you, Professor Fiorini. There are a few more questions. If you have the time, maybe you can answer to them. But we'll like to stop here. And I think Professor Fiorini is there. You can send him questions. Okay. And as per his time, he may answer. So thank you once again for your really educative and futuristic talk.
It's been a pleasure, and I hope you enjoyed my talk.
Yeah, thank you. I have one final question for you.
Yes,
a rather personal question. You had told me many years ago, decades ago, that your dream is to take over Da Vinci, make a better robot. How far are you in your dream?
Well, back and forth. So you mentioned that I started a company many years ago that didn't have enough support, so that I folded. But I'm starting another company just these very days, and I put together a small consortium of company and designers, and to try to do something. But again, with the idea of doing something that is at least 10 times cheaper than the Da Vinci. So we'll see if we can make it.
Okay, we wish you all the best.
Thank you very much.
Thank you, Professor. Thank you. It was very nice talk. Thank you.
Thank you very much for inviting me.
Thank you.
All right.
So we have the next session, which is session number 6 for poster presentation. So all the poster presenters, the first 8, paper number 66, 81, 112, 117, 99, 102, 53, and 95, you please come on stage. Okay. So one by
I'm
one,
adding one by one.
Yeah, one by one we'll be bringing you to stage. And please note that poster presentation is for 7 minutes. Please present the main topic of your poster as per the instructions given for 7 minutes only. Please keep the time constant, okay? Now, a couple of other points is that after the poster presentation, because we do not have a very detailed question and answer session here because of lack of time. So in the floor area, general floor area, you have been assigned tables. So if anybody wants to talk to you or interact with you, please, after the poster presentation, please go to the floor area. This is the floor area. And there is a table number and your paper number. Okay, so just look for your paper number and the table number there. So the table number is actually your paper number, sorry, the other way around. Okay, so in the floor area, after this presentation is over, you can go and sit in that corresponding table, corresponding to your paper number. And if anybody wants to ask you a question, they can come there and they can ask you the question. Okay? I hope that's clear. Okay.
So you'll have to double click on a table to enter a table. And the people who want to listen to you, they will have to come to your table, double click, and then they will be in your table. So please keep your webcam and mic turned on for all interaction. And on the right and left side, there are links to the posters. So if you click on a particular number, you will be able to go to a PDF online and you can just browse through it. And obviously the person who is on the poster, they will also be displaying their work when they talk to you.
Okay, so after the presentation, please, after the presentation is over, that means at 6 o'clock, you can go and sit on your corresponding table. Now, each presenter.
I'll just take one photo.
Yeah.
Can you please turn on your webcam, all the people on the stage? Okay, smile. Okay, done.
Okay, so please stick to the time, 7 minutes for each speaker. And we may have one or two questions at most. But after that, interaction is in the floor, okay, in your corresponding table. Okay, so the first speaker is paper number 66, Shubham Bhandari, design of robotic hand and wireless glove to teleoperate.
Yep.
Could you please share your screen?
Visible? Hello?
Yes, you can.
Yeah,
Sir. Please.
yeah, you're audible and
Visible? Okay.
yeah, everything is visible. So yeah, you can start. Please start.
Okay. So, good afternoon, everyone. My name is Shubham Mandari, and I'm here to present a paper on design of robotic hand and wireless glove to teleoperate. Now, as you all know, that robots have become an integral part of our work culture now. These are robots are being deployed in our everyday task where the situation may be hazardous to human life, or maybe it cannot be accomplished by a human hand. So in such cases, mostly we have the robots are able to accomplish the task, but there are certain situations where a programmed robot cannot perform that operation, and there is a human intervention required to help the robot out in such cases. So uh, to help out in these cases, to perform these operations where the nature of operations is really complex, there have been certain advancements in robotics where we are operating the systems using joysticks, spaceballs, or maybe computer vision. Now these systems are good, but we can even improve on the system to provide a better interface to the user, so that actually we are not genetically programmed to use joysticks or controllers, but we are programmed to use our hands. So we try to develop a system where we can control a robotic hand using our own hand by moving our own fingers, and that will be mimicked by that robot in near about same time. Now, we developed a robotic hand, and this can be controlled using a wireless glove. The robotic hand is composed of servo motors, batteries, and communication sensor, and these all sensors are controlled using an Arduino microcontroller. Now, all these electronics sit in the forearm of the robotic hand. This can be controlled using using a wireless glove that is worn by the operator. Now, again, this glove comprises of 5 flex sensors corresponding to the 5 fingers of the human. This is again controlled using an Arduino board, and we have an NRF24L01 plus sensor to communicate with the robotic hand. Now, this novel controller registers the user's input and transfers it to the actuators, which again in turn perform the corresponding operation. Now, as you can see in this image, we have the robotic hand and the wireless glove. So, to just sum up about the working of the system, as soon as a user wears this glove and he flexes or maybe relaxes his fingers, there's a change in the resistance of the flex sensors. This is registered by the Arduino board present on the glove of the user. This is then communicated to the robotic hand using the receiver, transceiver, sender, and receiver sensor. This robotic hand then uses that data to convert it into the angles through which a servo motor will rotate. This servo motor will then flexes these fingers. Now we have an elastic mechanism in the opposite direction, which is used to relax the fingers. Now, there's a small video about how the system works. Now, as you can see in this system, near about mimics the action in near about same time. There's a very slight delay. Now, the robotic hand demonstrates the working of teleoperated system where a user is sitting far away from the actual uh, location, and he can control the robotic hand from that distance. Now, from our experiments, we concluded that the NRF24L01 plus sensor was quite robust in this operation, as it was able to transfer data at a very low energy and also very high speed. So it was about nearly instantaneous. The action that is performed by the user is nearly instantaneous communicated to the robotic hand. Also, the flex sensors were quite robust to measure the change in the fingers of the user. Now, there's a graph on the right hand side where you can see that the this graph shows us the action that the user performs and the action that the robotic hand performs in seconds. So, as you can see that the robotic hand is working at the same time as the user is performing the action. Now this act as a extended part of a hand that is working at a distance. So even if you are sitting at a distance from a particular situation, you can control the robotic hand there and can perform the operation there. Now it can be deployed while handling harmful and hazardous substances, which a human hand cannot tolerate. So this robotic hand will be able to use and perform operation on those particular system. It can also be used in bomb disposal and handling radioactive substances without any threat to human life. Now this we try to develop a system where the controlling is as intrusive and as seamless as possible. Since we are easily able to control our hand, we will be easily able to control the robotic hand also. Now, there is nothing to learn in the system. You can easily do it by wearing just an operating glove. Now, this also acts as a proof of concept, and this can further be improved by using force-based control and also by providing haptic feedback to the user so that he can perform operation accordingly, and it can become even more seamless for the user to perform in such situations. And that's it from my side. Thank you, and I'm open for any questions.
Okay, thank you for your presentation. You have finished in 5.5 minutes, which is great. Now, I do have a few questions. Yeah, you can remain in your slide. You needn't come out.
Yeah.
Okay. So the first question I had is that have you done any kind of error analysis? Flex sensors are not very reliable. So there is chance of very high error between your glove and your robotic hand. That is one. Have you done any kind of error analysis?
Yeah, error analysis is in currently development. So this is a proof, a proof of concept, and we'll try to improve the system with better sensors and better code.
Yeah, because if you look at your video,
Yeah.
can you go back to your video?
Hmm.
If you look at the gloves, the index finger and the middle finger are straight in your gloves. Look at your gloves. The index finger, middle finger are straight, but the robotic hand has bent fingers. So
Yeah.
there appears to be some kind of mismatch going on.
Yeah. Actually, there's a little bit issue with the elastic mechanism. The elastic placed on the other side has malfunctioned a little bit.
Okay. So these things you need to look at, but it's a nice, interesting idea. Yeah.
Thank you,
Okay.
sir.
Thank you. Thank you.
Thanks a lot.
Thank you. Next speaker is paper number 81, Vignesh Sompur. Design and development of a bio-inspired novel three-fingered gripper platform. Is he there? Vignesh?
Is my screen visible?
Yeah, you can come on full screen.
Just a clarification to some people are asking when we will be going to the networking area. So after all the presentations, we'll go together. So we'll coordinate that. Please be here only.
Okay, so please be there till 6 o'clock. Okay, yeah, please start.
Okay, I'm be using the reader view since the full screen is not working.
Yeah, no
Okay.
problem.
Good afternoon, everyone. I am Vignesh Sompur, and I'm pursuing my PhD in IIT Madras in the field of biorobotics. My PhD advisors are Professor Ashokan and Professor Varadan. I am be presenting the work titled Design and Development of a Bio-Inspired Novel Three-Fingered Gripper Platform. Human hand has been the inspiration for robotic hand design for many decades now. This is mainly because of the immense dexterity that the human hand possesses. So because of the dexterity of the human hand, we are able to do multitude of tasks with fairly good comfort. So with human hand as the end goal, a preliminary step has been taken to improve the dexterity and versatility of a three-fingered gripper. There are numerous hands in literature which are publicly available. So broadly, they can be classified based on the number of degrees of freedom that they have, the transmission mechanism that they're employing, the number of fingers that they are designed for, actuators, and the applications that they are intended for. Though there are plenty of fully actuated hands, that means the number of degrees of freedom and the number of actuators that they possess are equal. They tend to be bulky, costly, and have complex architecture. So it is very difficult to be commercialized. So under actuated systems are generally the way forward, unless we develop architectures which are simpler. So under actuation can have anywhere from 1 motor to n motors, where n is less than number of degrees of freedom. The fingers on the hand can be driven using linkages or tendons. Though tendon-driven hands are compact in nature, they have less force at the fingertips, as well as they have backlash issues. So generally linkages are preferred, even though they tend to be bulkier. The number of fingers in the hands can be from 2, 3, 4, 5, or sometimes even 6 fingers are being developed. Though 5 fingers are preferred for prosthetic applications, 3 finger hands provide the good compromise between complexity, cost, and as well as dexterity. So 3 fingers are fairly simple systems. Actuators, electric motors, servo motors are generally used, but there are other hands which use pneumatic muzzle shape, memory alloys, hydraulics, etc. So it depends on what is the application. So the problem that we'll be handling will be to develop an under-actuated linkage-driven hand, which is low cost, and it is inspired from the structure and function of a human hand. To design the hand, including the wrist platform, data analysis has been done extensively. So a human hand grasp dataset has been, which is publicly available, has been used. It is observed that among all the 3-fingered grasps that are possible from the human hand, tripod grasps are the most stable because they provide the perfect compromise between precision and power. So tripod grasp is used as the reference. So anatomical positions of a completed tripod grasp is used to locate the fingers on the wrist platform. So once the wrist platform is designed based on the other anthropomorphic parameters, the fingers are designed. Standard 2-phalange finger, which is linkage based, is used. It contains 2 degrees of freedom. One is active and one is passive. The passive degree of freedom is provided by the spring. All the 3 fingers are actuated by a single motor, hence the system is under actuated. Both the phalanges are assumed to be of the same length, and care is taken such that the total finger length of the index, middle, and thumb is maintained to be anthropomorphic according to the grasp dataset. To find the link lengths of the other linkages in the mechanism, standard loop closures and Freudenstein equations have been used. Static analysis also has been performed to size the actuator as well as to determine the spring stiffness. So determining the stiffness of the spring is critical because it also provides the compliance that is required during grasping. So the parameters required for all the analysis here are again obtained from the grasp dataset. To transfer the motion from the actuator to the fingers, grade train mechanism has been developed, which consists of a lead screw, rack, and pinion. The lead screw pitch has been designed such that one rotation of the servo motor is sufficient for the entire trajectory of the fingers. The gear ratios for individual rack and pinion of the fingers are made such that they move different lengths based on the human grasp dataset. So this provides sort of differential motion for the fingers, which is providing an adaptive grasp. The CAD model of the assembly is as shown in figure 5. Preliminary experiment was made using a 3D printed model, which was built using PLA material. Common objects were used for grasping, and a dynamic axle servo motor was used for the experiment. In conclusion, a 6 degree of freedom gripper platform based on tripod grasp has been proposed. Human grasp data, which is publicly available, has been extensively used for the kinematic and static force analysis. The fingers designed also provide compliance for stable grasp. there is still work to be done on this model to prove the efficiency and advantages of this over conventional 3-finger gripper, which has fingers aligned at 120 degrees to each other. Also, the force sensors or haptic sensors can be added to make the grasping process more automatic. Movable wrist platform can be integrated so that it can be used in prosthetic applications in case it is required. Thank you.
Okay, thank you for your presentation. There are a couple of questions in this. For example, you are saying 6 degrees of freedom. This is 3 active and 3 passive, right?
Yes, sir.
Okay, that is one question. The second was, in your link length, did you do any kind of optimization in that 4-1 loop closure equation?
I validated once using analytical method and one using geometrical approach. So optimization was not done technically. A geometrical based approach was used so that we can map the trajectory that is obtained from the human grasp data. So
yeah, so that's my question. That are you following the human trajectory, fingertip trajectory?
Fingertip trajectory, not the individual joints, because we have 2 joints for the phalanges for human grasp, and here there is only single joint. So only the fingertip trajectory is being used.
So you are doing basically motion synthesis, right?
Yes, sir. Motion synthesis. We're using precision points, which can be obtained from the trajectory. So,
how many precision points you have used?
3 is sufficient.
3 points. Okay. Okay. I think that's all. Okay. Thank you. So the next author, please.
There are questions. I'll be answering the Q&A in the chat window.
Yeah. Yeah. Okay. Thank you.
Thank you, sir.
Chat. One question.
Next 112, Pritesh.
Next
Yes,
is
sir.
112, Pritesh.
Yes, sir.
Non-assembly 3D printed anthropomorphic hand prosthesis for low-income countries. Something very interesting happened now. So the speaker in his computer, it was showing the battery low power is going to shut down. I was thinking my computer is going to shut down. I was checking my connection. Okay, so yeah, so Pritesh.
Yes, sir.
Yeah, you can start your presentation.
Okay, sir. Good afternoon, everyone. My name is Pritesh Chhajar. I am an MTech student at IIT Guwahati. I'm here to present our work titled Non-Assembly 3D Printed Anthropomorphic Hand Prosthesis for Low-Income Countries on behalf of my co-authors Hirajyoti Basumatari, Mantu Kaibarta, and Professor Shamanta Moni Hazarika. So prosthesis and orthosis promise for people with physical or functional impairment to live productive, independent lives and encourage social inclusion. So according to the statistic by World Health Organization, there are around 40 million amputees around the world, and only 5 to 15% of them have access to the prosthetic and orthotic devices. So the motivation is to design a non-assembly prosthetic hand for amputees with upper limb dysfunction in low-income countries. So the non-assembly mechanisms are the mechanisms whose fabrication doesn't need an assembly step. This can reduce the need for skilled labor and decreasing the post-processing cost and hence decreasing the overall cost. So for this, we have looked at different existing linkage-based mechanisms and their potential of being converted into non-assembly mechanisms and then arrived at our own mechanism. We have followed the guidelines stated in literature while designing the 3D printing and non-assembly of the prosthesis, also keeping in mind various aspects like backlash clearance, providing fillets to alleviate the stress concentration, anisotropy generated during the 3D printing process, etc. So the low-cost prostheses that are commercially available in the market are either passive prostheses or body-powered prostheses. And electrically powered prosthesis still eludes the masses. So the objective is to design an active multi-articulated anthropomorphic prosthesis, keeping in mind the need of developing countries like India. So First, we have designed a tendon-driven prosthetic hand using the average anthropomorphic parameters, and then arrived at a non-assembly prosthetic hand using the same dimensions. So based on the anthropomorphic parameters, we have arrived at an under-actuated hand design. These are the designs of various phalanges of the fingers and thumb. The first 3 rows shows the distal phalanx, middle phalanx, and proximal phalanx of the fingers. And the last 3 rows shows the design of the thumb, the distal phalanx, proximal phalanx, and metacarpal phalanx. This is the assembled CAD model of the tendon-driven prosthetic hand. We can see the different phalanges and joints in the figure shown. So there are 1 motor to actuate each finger and 2 motors for the thumb. This is the 3D printed and assembled prototype of the tendon-driven mechanism. So we have then looked at different mechanisms to take this design towards a non-assembly mechanism. We have restricted 1 degree of freedom in each finger at the DIP joint between the distal phalange and the middle phalange. Even though we have reduced the number of degrees of freedom, using linkages, we have ensured a better force transmission as compared to tendons. And this is the assembled CAD model showing the Whippletree mechanism that we have used to actuate the fingers, and a rack and pinion mechanism for the thumb. This is a light-dependent resistor-based sensor developed by our team at Braille to sense the muscle contraction and actuate the non-assembly prosthesis hand through the Whippletree mechanism and the rack and pinion mechanism. So these are some results. These are different graphs visualized to observe the effectiveness of Whippletree mechanism. On the right, it is the 3D printed prototype that we have printed using fuse deposition modeling. And this is the sensor sensitivity plot. We have performed a power grasp 5 times and recorded the sensor output voltage. Each peak represents 1 power grasp. And so we have fabricated the anthropomorphic hand based on a non-assembly mechanism. So most of the multi-articulated non-assembly hands reported in the literature have only 1 degree of freedom per finger and a fixed thumb. So we have tried to provide an additional degree of freedom per finger and a thumb that can also be flexed to improve the articulation of the prosthetic hand. So the present work can improve the accessibility of hand prosthesis for low-income countries. However, more rigorous analysis with regards to play and backlash and their effects on grasping is to be done. Also, analysis of grip forces is to be done, and this is the part of the ongoing research. Thank you.
Thank you for your presentation. You're saying this is a non-assembly, but you still need to do assembly on this, right?
No, sir. The hand is printed. We have assembled it in SolidWorks and printed it as an assembled model.
Okay. How do you make the joints? The joints in
yes, sir. Yes, sir. We have provided some clearance in the joints so that while 3D printing, the engaging parts do not fuse together.
Okay. Yeah, so this is a great design. Now, what in terms of actuation, you're using normal cable-driven actuation, right?
Yes, sir. In the first model, we are using tendon-driven mechanism. Yes.
Okay. And 1, 2, 3, 4, 5 motors, so 5 degrees of freedom.
Yes, sir.
Okay. Now, because each cable is driving 1 finger,
yes, sir.
Can you grasp different kind of objects, or there is some limitation there?
In simulation, sir, we can grasp various types of objects. So the main focus is the 5 different types of grasps: the power, precision, cylindrical, oblique, and the pinch grasp.
Okay, so independent joint angles of the fingers cannot be controlled, right?
Yes.
They are coupled. Okay.
Yes, sir.
Okay, thank you. Okay, thank you very much.
Thank you, sir.
So he was Pritesh.
Next, do we have Parthan?
Yes,
Next is paper 117, Parthan.
Yes, sir.
Manikesaran.
Manisekaran, sir.
Manishekaran.
Am I audible?
Yeah, you have to be a bit loud.
Hello.
Yes.
Am I
Yeah, we can
Yes.
hear you. Yeah.
I'll just talk like this. Yeah. Good afternoon to everyone present here. I am Parthan Manisekaran, BTech from PS University. We have worked on this project from the Center for Robotics and Automation and Intelligent Systems. And our project is called ARMOR, Modular and Semi-Autonomous Supernumerary Robotic Limbs for Disaster Relief. It might sound a mouthful, so I'm going to get into the details later. So why did we actually come up with this particular application? We came up with this application seeing the challenges which were faced by the NDRF team during the earthquakes and floods and other calamities. One important work which they need to do consistently is to lift or push objects multiple times under different uncertain conditions. And use of technology can be one way to help them out. And this is one such attempt. So while SRLs have been there since 2012, most of the SRLs actually work on a known environment and with known conditions. So these SRLs have been used for sealing work, for balancing, for rehabilitation. But since we are mainly focusing on a disaster scenario where it'll usually not be a known environment, we are looking at a different concept of working. So the existing SRLs use something called a leader-follower base, wherein the robot is either programmed or is shown how to work and the robot just follows it. But here, since we are looking at an uncertain condition, we are taking the use of computer vision for the functioning. And finally, we are looking at pushing as our priority here, as compared to other papers which usually work towards balance and lifting lighter objects. So what are we trying to do here? So we are trying to build an SRL-based suit which can push objects of different sizes with minimum intervention from the user. We want to make sure that the user does not spend more time in controlling, but rather can spend time in just telling the command and the robot does everything on its own. The next thing is the robot should be able to detect or recognize the target, that's the debris which needs to be pushed, and if there are any obstacles, to avoid collision with the obstacle. So in a disaster site, you usually have many people working simultaneously, and you do not want to hit them when you're working. So you have to make sure that we are looking at the target as well as if there are any obstacles present. And since we are not looking at the research lab sort of scenario, but something where portability is important, so we are working towards making it portable and easy to use for the NDRF teams. And finally, we do not want to develop SRLs, different SRLs for different functionalities. So we are trying to work on just replacing the end effector and adding multiple functionalities inside the arm. So how we went about this? So first we considered an average human height to be about 5.6 feet, and the waist height would come up to about 3 feet. And we set a constraint that about 75 centimeters of ground span is what we need the robot to move to. So with this calculation, we were able to get the arm to about 110 centimeters. So now what we did was, instead of taking 110 centimeters, we scaled down the model for two reasons. Firstly, we wanted to make sure that the proof of concept works out. And second thing is it will be a little cost effective. So the materials which we have used here, which we were planning to use, which we have used here are CFRP and ABS. For the original model, we had the proposal of CFRP, which is carbon fiber reinforced plastic, due to the fact that it has a good high strength to weight ratio. But then for the scaled down model, again, since it's a proof of concept, we use ABS and we 3D printed it. So the reason why we chose 3D printing as a method here is because since we are looking at a dynamic situation where there are high chances of quick prototyping or quick production of these arms, so hence we thought of giving 3D printing an approach basically. And next we have developed a modular design wherein if any one of the part breaks, you just have to replace that particular part, and there's a way to extend the arm itself due to the modular design here. And again, like I told you, the end effector can be replaced depending on which functionalities are required. For now, we have had the pushing action. We are looking towards other actions like pulling and lifting or even drilling actions. So we have used high torque motors. We have used 3 high torque motors for a pitch action and 2 yaw motions for pushing the debris. So we've used ROS as our entire control framework, starting from the path planning for the arm all the way to the Arduino controls for the motor. And finally, we've used RGBD, that is red, green, blue depth cameras, for debris location and obstacle avoidance. So what we first did was we did the stress analysis on a scaled down version of the model. So we have considered 3 different loads, 5 kgs, 3 kgs and 2 kgs, and we have calculated the maximum stress, total displacement and factor of safety. So here what we found is at around 2 kilograms, the factor of safety comes about 1.61, which we fixed as the maximum, and we did not want it to go beyond that for our particular application. And we've calculated the DH parameters, forward kinematics and inverse kinematics of the arm. So we were able to detect the depth of any object in front of the RGBD camera, and it was able to get the exact coordinates in the 3D space. We've used the YOLO model for detecting obstacles to avoid collision, and we've used MoveIt and Gazebo as our simulators for the path planning and simulation to move the end effector to a particular point in space. And finally, we had fabricated it using ABS, and we were able to push an object of about 1.5 kgs. The graph here shows the displacement curve for a simulation of 20 seconds, wherein the first graph basically depicts the movement of the first link, which is the pitch motion, and the 2 graphs are the yaw motion for pushing the object. So this is, to be honest, this is our initial results towards this concept, and due to time and resource constraint, we've come this far. The use of the scaled down version helped us understand numerous abilities of what we are building and also the shortcomings of the work. We are working towards the second version of Armor, wherein we are looking to implement better materials, designs and functionalities. And we are not just looking at it from a research perspective, but actually to a production level. So hence we are focusing more towards a user-centric approach, wherein voice control or virtual reality headsets can be used for making it easy for the person to use it. This will be converted into a production-grade design in the near future. Thank you very much.
Okay, thank you for your presentation. A few questions. The first is what is the total weight of the system, because the person is wearing it, right?
Yes, sir. So the scaled down version of the arm came up to about 1.08 kgs to 1.2 kgs, sir.
That is with motors and battery and everything.
With motors and the arm, sir. The battery we are using AC supply for now, so we haven't considered the battery. But if you were to consider the battery, it would come up to 3 to 5 kilograms.
Yeah, because that is a major component in such designs.
Yes,
the power
sir.
source.
Yes, sir.
Okay, that is one. The second is that there are 3 degrees of freedom on each arm, right?
Yes, sir.
So 336 you have. Okay. Yeah, and how is the drive? Is it cable driven or is it direct geared?
It's direct gears, sir, actually, for now. But that's the whole reason, sir. We have used 650 kg centimeter motors, which are high torque, and hence the power supply which is required for it is more. So we are looking at more of a cable driven or a better way of transmitting torque for now.
Okay. Okay. Thank you. Thank you for your presentation.
Thank you, sir.
The next presenter is paper number 99.
Bansal Kumar. Bansal Kumar.
And it is by Bansal Kumar, right?
Yes.
Yes, sir.
Yeah, Bansal.
Let me share my screen. Hello.
Yeah, we can see. You can start, please.
Okay. So, good afternoon, everyone. As the research work is titled "A Deep Learning-Based Real-Time Computation of Thrust for Fish-Inspired Robotics." The motivation against this project was due to the various uses of fish-inspired robot in inspection, discovery, military intelligence, and improving reach in areas such as pipelines, etc. And for the same, it is important that the robot can perform all these tasks with minimum human intervention, that is in a fully autonomous way. And this can be achieved by a proper motion planning algorithms. As per now, motion planning can help in a stable environment, which is fixed, but we know that in a natural habitat, that is not possible. So we are intending towards a real-time based motion planning approach that can act and try to adjust to the changing environment. In the literature review, we have been through several works, some of which include the motion planning using simple equation of motion and force balance. These are fast methods, but with a lower accuracy. The next set of work includes CFD-based tools that are almost perfect in accuracy, but are very slow and cannot be used in real-time computation. So we are trying in this work to use a deep learning-based method so that we can get the time of the first counterpart and as well as accuracy of CFD-based method. This takes us to our problem statement, which is to make a tool to compute thrust for a fish-inspired robot in real time using a given set of inputs and parameters, which are as presented on your screen. The variables include the motion parameters such as tail beat frequency, amplitude of flapping, because we consider the motion of the fish to be an SHM. Apart from this, we also go for velocity of water and orientation of fish with respect to environment to give the relative velocity against the flow. And to get the results in real time, we go for orientation of angle of fish tail so that we can know exact at which orientation, what is the force that we are getting. And that leads us to the final variable, that is thrust, which is going to be our output. In the same word, we have put in some fixed values such as density and fish geometry, which add parameters for this word. Moving on to the methodology part, once we have decided on inputs, we need to discretize the same to use and go through all the process. As you can see on screen, we have taken a range from some work already published and then made step size so that we can work with higher accuracy as well as maintaining as small overfitting as possible in the neural networks. Once the data is discretized, it goes for CFD-based computation. On the right-hand side, on top, you can see the geometry that we are using in this project. It includes a fish robot, which is surrounded by cuboidal mass of water with a velocity inlet in front and pressure outlet at the back. The same is when a mesh can be seen in the figure downwards, where the mesh is coarser across the boundary and finer near the fish robot to maintain accuracy as well as speed of computation. The same was validated against the work of Kumar and Shirin in their work because the approach was similar and the geometry was same. As you can see, there are some irregularities. This is mainly because even though the work is similar, the methodologies used are not exactly the same. And on further inspection, we concluded that these irregularities were increased when we went on to go in an extreme condition of environment, that is higher values of the variables that we had. And such was only constrained to 10% of the total data set. Similarly, we also made a grid independent study to see if the element size of our mesh affected the results. And as per the graph, you can see that has the minimal effect. So we went on ahead with the training ANN model. The image on the left side represents the physical demonstration of the ANN model, which includes of an input layer with 5 neurons, 2 hidden layers with 10 and 5 neurons, and an output layer that is thrust in perpendicular and parallel direction of the fish. Using these, we have also taken the epoch to be 1000 and batch size of 64 to the results as per the right-hand side table. That is coefficient of determination of 0.97, that is quite good. And the error value is being very low, also presented in the table itself. After training, to get to these results, we had to optimize the model various times and do several tests. This was done by using the weights method as per the work of Gebre and his team. And it concluded with the orientation of fish, that is the direction of relative motion between the flow of water and fish being the most important variable. And thus we were to train it such that we can get maximum precision in such areas to get to the results. Similarly, this is the entire workflow, summary of workflow, and we can head to the result, which was done into a two process. First, we used the set of input parameters, and we got results for them in CFD and in ANN and plotted together in a graph. And as you can see, it gives the coefficient of value of 0.8 that is acceptable at this part. And the next comparison we did was in a path following manner, in which we gave an initial state to both the robots and left and calculated it using CFD and the ANN model that we developed, in which the error that came out to be was 6.42 in comparison to CFD, but the computation time decreased drastically. So in conclusion, I can say that this approach can be a viable option when we try to go for a real-time computation. And also stating the limitations, this approach, while in general can be applied on different geometries and densities, it has only been taken fixed in this work. And also this doesn't consider any physical losses or inaccuracy while measuring of the input variables in the surrounding, in the environment as well. So the future work includes to incorporate various geometries and densities as variable rather than parameters, and also to test and validate the results on a physical platform. So that would be it from my side. Thank you, and I'm open to the questions, if any.
Okay, thank you, Bansal Kumar, for your nice presentation.
Yes,
so what I understood is that you're using CFD, you're using what, Fluent or?
Fluent. Oh, sorry, I forgot to mention that. The same was used using Fluent, ANSYS Workbench and Fluent for this work throughout this work.
Okay, and the fish is only changing direction, right? It doesn't go up or down.
No, sir. That is one of the limitations of this work, that we are only assuming a fixed density and a depth of the fish at this moment in time.
And the fish also doesn't have degrees of freedom, right? It's a solid object.
No, sir. The scale of the fish goes through an SHM process, and that is done through the UADF command in ANSYS Fluent.
Okay, so the tail has 1 degree of freedom, right?
Yes, sir. It is undergoing SHM.
Okay. 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 Thank you for your presentation.
Thank you, sir. Thank you, everyone.
It will be interesting to do the experiment and actually compare. That will be interesting. So our next speaker is
Bharat Raja.
Bharat Raja, multi-layer perceptron-based classification of recyclable plastics from waste using hyperspectral imaging for robotic sorting.
Yes, sir.
Is he here? Yeah. Can you please share your slides?
Is my screen visible, sir?
Yes.
Yes, they are visible. Yes, you can start.
Good afternoon, everyone. I am Pedapudi Bharatraj Bhupal, MTech student from Mechanical Engineering Department, IIT Patna. And my research topic is on multi-layer perceptron-based classification of recyclable plastic from waste using hyperspectral imaging for robotic sorting. And the co-authors are Dr. Subrata Hayat, from Associate Professor from Civil and Environmental Engineering, IIT Patna, and Dr. Atul Thakur, Associate Professor from Mechanical Engineering Department, IIT Patna. And my motivation towards this research topic is, if we get into the stats of the waste generation, we can see in low middle income countries, waste generation spiked up to 3 times. So this will be helpful for our country because a lot of our population comes into this category. And in this waste generation, plastic contributes about 10%, which is more significant. And since we can't reduce the usage of plastic, recycling is the viable solution. So this can be accelerated. This recycling process can be accelerated using by imparting automation into the process. With the help of hyperspectral imaging, we will do the classification of the different kinds of plastic for recycling process. In the literature review, there are many research work done on this area. Initially, thermal imaging techniques are used for broad classification of waste stream, where it will classify objects into metallic and non-metallic fractions. And later on, it shifted to hyperspectral imaging, where it extracts more information from a scene. Then using the region, selecting the region of interest, and extracting features using similarities in the pixel spectra, uh, we can predict the infectious portion of the fruit or maturity grading in the fruits or vegetables. And a lot of applications in remote sensing area using hyperspectral imaging is done with the help of deep learning models like convolution neural network and autoencoders. That includes the spectral and spatial features. And coming to our application for plastic sorting, there are few architectures that are used like UNet and ResNet 8, but these are limited to these are like a transfer learning kind of operations. So we need to develop uh, uh, a robust classification algorithm for plastic sorting, since the research area in this field are very scant. And our problem statement come to be like we have to extract features from the hyperspectral image so that we can identify what kind of plastic it is, and later on it is sent to the robotic manipulator, where it will do the pick and place operation into their respective kinds of bins. In methodology, there are 6 steps. First step is sample preparation. Uh, we prepare samples using 5 kinds of plastic: HDPE, polystyrene, PET, polypropylene, and PMMA. These samples are collected from the household waste, and these labels of this plastic were obtained from the resin codes that are back on the items. And here are the samples that we have used for our data preparation. Uh, these items are trimmed off so that it can fit into the field of view of the camera. And in the next step, image acquisition, we can see the experimental setup of the image acquisition, where hyperspectral camera records the scene in spectral range of 700 to 1900 nanometer with 168 spectral channels in 14-bit bit depth. So in total, 35 hyperspectral images were taken. In each hyperspectral image, there were 10 objects chosen randomly, and those were placed and oriented randomly. In pre-processing step, we will do the flat field corrections. This will take care of the non-uniform illumination and sensor noise. It will be applied according to the formula by calculating the relative difference using the white diffuse reflectance and dark current obtained from the camera. And these corrections were already made by the SpectralOn Pro software that comes with the hyperspectral camera. Here are the sample images, hyperspectral images, shown as a pseudo RGB images. Uh, Now these hyperspectral images will go to the clustering operation. There we will calculate the entropy of the image so that it will separate the foreground and background easily. Since the contrast is very low, we will employ image enhancements like normalization and power law transformation, and later on thresholding. And noise filtering is applied to remove the unwanted artifacts in the image. And at the end, we will apply morphological operation and region labeling for extracting different objects in a image. And at the end, classification is obtained by, once we got the clusters from the hyperspectral image, we will calculate the 4 features from each band. So in total, 168 bands means 672 features. We'll calculate, and we will implement PCA for dimensionality reduction. And we will train the neural network using Adam optimization with a softmax output. And we will validate this neural network using accuracy and and by tuning other hyperparameters. And once we are ready with the neural network architecture, we will train and we will test. At the end, we will get the labels and the position of the object, and we will send this to the robot manipulator so that it will do the sorting operation. Actually, this sorting operation is the future work of this research. And in the results section, we will train the neural network with 294 hyperspectral images and 56 as testing data set size, and we got the accuracy of 96% on training data and 98% on testing data. Here is the confusion matrix for the testing data, which is closer to the ideal confusion matrix. It should contain only diagonal elements, but there is one misclassification of PET material, as we can see. So the error metrics of F1 score are almost close to 1. So the model is robust enough for the classification of these plastic materials. Conclusions are clustering operation is robust enough for our image data set, so that we got accurate clustering operation. And the statistical moments that we derived along with the PCA implementation of dimensionality reduction helped in modeling the neural network. So we got good metrics of accuracies of about 98%. And so we are able to classify these 5 kinds of plastics accurately. And the automatic sorting is done at the end with any kind of test image that we do. And future work is related to the adaptation of the algorithm to overlapping objects and implementing sequencing algorithms for optimal sorting.
Okay, thank you for your presentation. Now the question here is that number one is you have put it in future work that if there are objects which are overlapping, then what will you do? That's one. The second is the image processing and things like that. You talked about entropy and background subtraction. They are you wrote the program, or they're all standard MATLAB codes?
Sir, for the future work, these overlapping objects, we can take care of that. Like if we are calculating, it can be taken care at the entropy calculation step. We can give threshold for if there is a difference of more than 0.5, we can treat those as different objects. So this is planned for the future work.
Okay.
And coming to the programming part, those entropy calculations were they don't have any standard functions, so I did the coding part. And those image processing operations, there are codes for morphological operations and thresholding.
Yeah,
for
so
those
that
I
is
have
in
used libraries.
OpenCV or MATLAB?
MATLAB, sir.
MATLAB. Okay, so another way in which people handle overlapping objects, they put it on a shaker and they shake it so that the objects are not overlapping anymore, they separate out.
Yes, sir. For this experimental setup, we can use the vibrators before the image acquisition part.
Okay, thank you. Thank you for your talk.
Thank you, sir.
So the next speaker is Hari Narayan, Nampur 3. He'll talk on MPC-based path planning for wheeled mobile robots in environments with varying slip. Yeah, we can hear you. Please share your screen and please speak a little loudly.
Hello, sir. Am I audible? Hello.
Yeah, can you hold it near your mouth so that it's a little louder? Yeah.
Okay, sir. Okay. I will share my screen, sir.
Yeah.
You may turn off your video because there's a lag. Harinarayan. You can turn off your video feed.
Yeah, Harinarayan, please turn off your camera.
Okay, sir. Oh, okay, sir. Okay. 1 minute, sir.
No, it's not sharing.
I will turn off my camera, sir. Sir, now my screen is visible.
No, not as yet.
Okay, sir. Let me share one more time.
Had you tried earlier?
Sir, what is step?
Yes, it is loading. You may please go to PowerPoint.
Okay, sir. Thank you. Okay.
Yes, okay.
Sorry for the
Yes,
inconvenience.
Yeah, please
Hello,
start.
sir.
Yeah, please start.
Thank you, sir. Good afternoon, all. Today, I am going to present a paper, MPC-based path planning for wheeled mobile robots in environments with varying. Okay, I'm Harinarayanan Nambudiri from a research scholar from APJ Abdul Kalam Technological University, Kerala. So our research motivation is to integrate the advanced learning techniques with this modern control strategies in the case of wheeled mobile robots. So quick recap to our literature review. So the machine learning has been a wide hot topic for researchers even in the field of wheeled mobile robots. One of the area is terrain classification. The first two papers are mentioning about that. It's our question to how you can use this terrain classification to the proper control of or improve the control performance of wheeled mobile robots. Then we check the state of art in terrain-based control. The terrain estimation, the parameters of terrain are estimated with the help of physical models. And the fourth paper, the Gonzalez paper, they're working for NASA Mars rover. They are working with terrain classification using machine learning, suggested slip estimation as an extension to the classification work. And yeah, then we that motivated us, and we look for good controllers, and we choose model predictive controller by researchers on controllers used for this particular purpose. So the problem statement is to design a model predictive controller that can integrate with this machine learning techniques to be used in wheeled mobile robots to navigate in varying slip conditions, including the factors of including the nature of terrains and other factors also in affecting the slip. Okay, the objective, the challenge in developing an MPC controller is to identify a suitable dynamic model that includes the slip values, and then we need to control the torque signals to the wheels. That is one of the another objective of this study. And the third objective is to test the controller design using simulations. So yeah, the methodology, the block diagram, the conceptual block diagram, you can see on the left side. For this work, this is a part of a project, and for this work, we are assuming that there is a machine learning model, there is a slip estimation model that can give 4 slip parameters to our MPC controller, and this MPC controller can act on it and modify the torque signals to the wheel. Okay, and this entire process is done on MATLAB. It is a simulation process. Entire process is done on MATLAB. The slip parameters we choose here is this 2 longitudinal slip parameters and 2 lateral slip parameters. This is the model we are choosing here is a differential drive robot. So the longitudinal as well as lateral slips of each wheel are considered. In the right side figure, the longitudinal and lateral slip, the parameters are represented. That is the longitudinal slip. This is not longitudinal slip. The longitudinal displacement, including the slip, is represented here, and the lateral slip is represented here in this pictorially. In the bottom, you can see the MATLAB MPC designer, in which 2 manipulated variables are going into the plan. They are wheel torques, and 5 measured variables are state variables that are actually modified using our modified dynamic model that are designed. So this model we have designed in our paper. Please, this entire derivation is done on our paper, and MPC is designed to minimize the error cost function of state variables. So regarding the results, so actually this is a simulation process. We are for validating our operation, we took different test cases for verifying the operation. This case 1, you can see there are 5 different. We tested both longitudinal as well as lateral slip cases separately. 0% case means both wheels are having no slip, and 100% means both wheels are happening with the higher slip conditions. Most slip condition is for 100%, and 0% is low slip case. We can see the linear velocity, the output from the linear velocity of the model. We can see it for low slip cases, no slip cases, velocity is changing smoothly. We are following a circular trajectory for this particular simulation. And for higher slip cases, we can see the velocity changes very slowly. And same we observed in the case of lateral slip also. Okay, together, so then we analyze the linear acceleration variations for together, both longitudinal as well as a lateral slip varied simultaneously. This means no slip in longitudinal as well as lateral case. And sixth case is the most slip. The sixth case is a condition which most big slip occurs. That means you can see for case 1, the slip without slip cases, so low slip cases, the acceleration is changing fastly. As a slip increases, you can see the acceleration kept on decreasing, and even it is going in some other direction. So this means as the slip changes, there is an effect on velocity. It's practically when we think the velocity changes according to higher slip is a good result, we think. So the conclusion is we developed a dynamic model that included slip parameters, and the MPC is designed and developed, and the ability of the control to address the slip parameter is evaluated. And in future, this work is in an assumption that there is a machine learning model that can give these 4 slip parameters in real time to the MPC controller. So in future, it has to be properly developed and this integrated with the MPC controller. So this is an appendix. This is the MATLAB. This is an overall MATLAB simulating model we developed. Thank you.
Thank you, Harinarayan, for your talk. Now, can you go back to your control system diagram? Yeah, there. So here you're saying the slip estimation model. Now, does the slip estimation or slip depend on things like terrain parameters?
Yes, sir. Not only terrain, but also the terrain variations in terrain definitely affect the slip.
So that is not being taken as input anywhere here.
Where, sir? These values.
Yeah, in this loop diagram. So terrain information is not being given to the robot, right?
No, sir. That slip estimation model, which is a machine learning model that can use any terrain machine learning model that evaluates the slip values. That depends upon different parameters, including this terrain and other change in this trajectory. So different conditions has to be learned. So from there, the output we are expecting is 4 slip values.
Okay, so you have run this robot in or vehicle in some kind of terrain. Have you done any simulation like that, or not as yet?
No, sir. This is done in only MATLAB. Only simulation is done in.
No, here the output is only velocity, right?
We shown the velocity, sir. Actually, it is passing through a dynamics. Actually, the MPC output is torque signals, and we check the velocity values for the validation of our work.
Okay. No, I'm saying that you did not run the robot on a terrain and see that it's actually running. That
yes, sir. I know.
Okay.
Yeah, no.
Then you'll know whether your slip estimation is correct or not correct.
Yes, sir. That is actually we just motivated from that Gonzalez work that they are saying that terrain is one influencing factor for slip variation.
Yeah, probably the most influencing parameter is the terrain.
Yeah.
Okay. Thank you.
Thank you, sir.
Now we have the next talk, which is Meghana, comparative study of inverse kinematics using data-driven and fabric approach. Yeah, can you share your screen, please?
Good evening, sir.
Good evening.
Sorry. Can you see my screen?
Yeah, you can come on full screen.
Yeah. Is it visible, sir?
Yes, please start.
Yeah. Thank you, sir. Thank you for giving this opportunity. I am Meghna. Azad National Institute of Technology, Bhopal. I'm pursuing my post-graduation there in computer science department. I have done this on guidance of Dr. Vijay Bhaskar sir, and Aditya has also my teammate in this. Here, the motivation that we got is in robotics. Now, in increasing technology, like robot has become very important in every field, in medical and everywhere. So in robotics, if we come, robot hand is the mostly used everywhere, in even cooking, in every application where robot is there, robot hand application is the highest we see. So in that, we could notice that the kinematics of robots are highly important. So solving kinematics of a robot has various methods in it, and there are a lot of problems in it, and we are coming up with two methods here. That is, one is using neural networks, and which is data driven approach, and the other one is fabric approach, which is an iterative approach. So we have seen like robot hand has different type of joints in it, and like different joint has like different reachable space for it, and there are many algorithms that are available, and many algorithms have a lot of computational cost, and there are very complex calculations like matrices, trigonometric involved in it, because of which it is taking high computational time to solve inverse kinematics using that methods. So here we are showing that the computational time and the accuracy can be improved using these two methods, where neural network can also learn how inverse kinematics is processed, and based on that it will give you the results, so that it will learn. So it will be easy, and computational will be very less. In fabric method, it iteratively do instead of calculating higher trigonometric calculations. So the main intention was to solve inverse kinematics problem. So why only? Because of computational time and complexity of the computation problems. So here we are trying to solve that using these two methods. So in neural network method, if we come, here the first problem is to generate data to train neural network method. To generate data, we, instead of using inverse kinematics where we have higher trigonometric calculations, we used forward kinematics, where the calculation part is easier and better than inverse kinematics. So using forward kinematics, we are trying to train neural network with inverse kinematic solution. So we have generated data using forward kinematics. We have given some random points of 10,000 points on a plane, and for that points we have calculated the joint angles using forward kinematics, and the complete data set is generated and it is given to neural network. And neural network we have trained on 70% of data, and 30% of is for validation and testing. And neural network that we used is a neural network in it, and one hidden 1,100 neurons in it. So neural network will learn inverse kinematics in that. Input will be here. The it will give me it will calculate as and give the trajectory points that we have to reach. So that is about neural network here. And fabric method is forward and backward reaching. That is an iterative method. If you see in this diagram, this dotted line shows the initial position of the manipulator. In this, if this is the yellow dot shows the target point it has to reach, it will assume that the final end effector has already reached to the target point, and it will, based on that point it has already assumed, it will be calculating new P3, P3 dash, P2 dash, and P1 dash. But because of we moved P1 dash from origin position, now it is also responsible to calculate new maintain the origin position as fixed position. So again we'll traverse in the backward direction and calculate new P1 double dash, P2 double dash, and P3 double dash. In the same way, it will move forward and it will move backward and try to reach position, that which shows the yellow dot. So in this process, it is just an iterative algorithm. So for the data that whatever we have generated, we have seen up to maximum 7 iterations it was taking in the highest case. So because the less number of iterations it has taken, that is because in the first iteration only it will be reaching very near to the target position. So it will not have to take longer iterations, because in the first iteration it is taking a longer step to reach to the target position. So we could achieve in less number of iterations. And also the accuracy, if you come with the tolerance, we could reach up to 0.001%, less than that value. So there will be very less error in the fabric method. And using these two methods, we are showing the applications or how a robot, how the robot behave if it write any patterns. So in the results here, if you see in neural network method, the green line shows the original pattern and the blue line shows the neural network drawn pattern. In the circle, if you see, there is some disturbance here in this points. Even we could write some letters like this, manet, robot. So there is some point of error in this. So we could achieve up to 97% of accuracy in neural network method. And the time taken for every process to draw is, this is the time taken in seconds. In fabric method, if we see here, there is no green part seen here. That means the green is completely replaced with blue, and there is no error here. It is almost near to 0, because the tolerance we could achieve up to 0.001. So there is very minimal error. There is like a negligible error in this, we could see. And the time taken for this to calculate and plot every pattern is this much. And it is taking little bit more time than neural network, because in neural network data is already created and it's trained on that. Here, for every pattern it has to draw, it has to go through that process because of that, but there is not much difference in timings that it affects a lot. So here we have seen two methods, and we could notice that the accuracy, if we compare, like fabric method is performing better, and even like time, that is not much different. So it is not very like big disadvantage in that. So it is good. Like we have fabric method applicable in many industries, we could see. And also neural network also we could get up to 97%. So in any cases, if we have like we can compromise with accuracy, we can go with 97% because the time constraint is less. So to improve further in this models, to train, improve neural network method, we can go with multiple hidden layers with a pattern of reducing number of neurons from layer to layer can improve the performance. We can, if any application, we can try with that. If we, as the number or degree of freedom and all increases, we can go with like deeper and deeper neural networks and try. And fabric, we could did not try with like multiple end effectors. We can implement that, trying with multiple end effectors and see how the performance can be. Yeah.
Okay, thank you for your presentation.
Thank you, sir.
A few questions is that you are considering basically a 3 degree of freedom planar arm, right?
Yeah, we tried for 3 degree of freedom, and again we extended this up to 6 degree of freedom.
Is it planar or is it special?
It is not planar.
Okay.
In this, yeah, thank you, sir, for asking. Neural network same neural network did not give the better performance for the 6 degree of freedom. We tried that, but fabric could absolutely perform in the same way for both, even after increasing the because even for us to do any new computation was also not required. Like the same code work absolutely fine with that. So
Okay.
for neural network to learn inverse kinematics for higher degree of freedom was a bit difficult. It did not able to learn it very appropriately. The error has increased than this.
Okay, my other question was that there are always this question of multiple solutions.
Yes, yeah. Multiple solutions. Neural network could in Fabric, if you see, multiple solutions is not possible because it will always to that position using the nearest distance it has. Okay. So the multiple solution problem here doesn't occur. I agree. In neural network, we are directly using inverse kinematics formulas only, like same thing it is. But even here, we could achieve the problem of multiple solutions because neural network is learning in such a way that when it is in one position, it is trying to obtain the next position which is very nearest to it. It is by itself learning that we tried doing experiments on that. That is because of we are training on very multiple data, 10,000 data, like it was trying to reach to the nearest point it has. If it has two positions, which is the nearest one, it is showing that as a result.
Okay. Okay. Thank you. Thank you for your presentation.
Thank you, sir.
Okay. And now we have the next set of 7 speakers. Okay.
Yes.
Let's take a break of 5 minutes. The next set of 7 speakers can come on stage.
Yeah, they're on stage. We need to check on the status of paper number 86. Do we have Deep Narendra or Shankar Karmarkar? I have added Shankar Karmarkar since he was one of the speakers. And also paper ID 43, Ravikant Jain. I've added him. So I hope 2, 3, 4. So how do we know?
Yeah, I'll just call them up. Yeah. So Deep Narendra, I'll just call him up. Yeah. So he had 79 and 86. So I'll just call him. 9, 4, 5.
Then Ravikant Jain. I have added him. Ravikant Jain, Dr. Ravikant Jain, can you please unmute?
Yeah, I'm here.
Okay. Will you be presenting for paper ID 43?
Yeah.
Okay.
Okay, I'll just call up Deep Narayan.
So shall I call you?
The Deep, you have a paper presentation now, no? Number 86. Not, yeah, but please join because we are going say 10-20 minutes before time. Okay, so yours is the fourth paper now. Okay. Okay. He was relaxing. His is a 5:30.
I'll just take one photo.
Yeah.
Okay, done.
Okay, I'll just come in 5 minutes. Then we'll start. You can take the presentation part.
Yeah, I'll just.
So we'll just come in 5 minutes. So it's 4:25. We'll start at 4:30. Yeah?
Okay, sir. So the people who are on the stage, you may please turn on your one by one. Maybe Shreyas can start. Try once. Share your screen and then you can stop. If you have tested it, the stream was unable to connect. That is something I see. How about others? Do you see his screen?
Yes, sir.
Others can see Shreyas' screen?
Yes, sir, we can see.
Okay. Okay, maybe I have some issues. Let me just Control-Shift-R. So maybe we can try with Piyush Taylor next.
Yeah, sure.
I don't see it yet. Okay, Dr. Deep Narayan Ray is also here. I'll just add him. Piyush, did you try?
Yes, I'm trying. Like it's been processing.
What does it say?
It says rolling and rolling.
Did you try there on the table outside? Have you tried it? Sharing the screen earlier?
No, sir.
You should have done, right? We had instructed. Aditi, please try. Yeah, so please go to PowerPoint or whatever slides you will be sharing. You can try full screen mode quickly. Okay, perfect. Thank you. Next, please stop sharing. Dr. Ravikant Jain, you may please try.
Yeah, we are ready.
Okay, sir. We'll start off. Another 2 minutes, maybe. Dr. Ravikant Jain, please. Okay, Piyush, I see you sharing. Okay, there seems to be some delay. Yeah, we can see it. Okay, you can stop sharing.
Okay, sure.
Yeah, Dr. Ravikant Jain, please share.
Yeah, here is working actually.
Okay, fine. Next, we have, I think Dr. Deep Narayan had already done yesterday. I hope it will work. Sudhanshu Ranjan, please share. Do we have Nakka Sanjeevi?
Yeah.
Okay, I think we are ready.
Okay, sir.
Shall I try sharing?
Yes, please. No, Sanjeevi Nakka, you had already done from in the morning, so that should be fine. Okay, sir. We'll start off.
Okay, the first speaker is Shreyans, right?
Shreyas.
Shreyas, page paper number 113.
Is my screen visible?
Yes, please speak a little louder.
Good evening, everyone. I am Shreyas Patel, currently working as a JRF in IIT Jodhpur. My topic of my presentation is motion planning of half humanoid in the presence of obstacle. The half humanoid is a robot which resembles the upper part of the human body. The half humanoid robot can be used to perform many tasks such as switch panel operation. It can also perform some communication gesture as well as object manipulation. And for that, it's need to path planning is required for all the operations. And recently, ISRO has also announced to launch a half humanoid robot named Vyomitra into space station under the mission of Gaganyaan. And so main objective of this presentation is to plan obstacle-free path planning for the approach phases. Also perform closed-loop motion planning in the post-graphing, which will be useful for object manipulation, and for perform a perfect
a dynamic analysis for both the cases, that open loop configuration and closed loop configuration, approach phase and post grasping phase. The methodology is that first we perform a dynamic analysis for approach phases. For that, in approach phases, open loop half humanoid has an open loop configuration. For that, RRT star is used to generate the path in the obstacle free path. Then after getting that path, continuous path planning is done to trace the trajectory of end effector to avoid the obstacle and reaching to the goal. After that, reaching to the objective, we need to move that object to the other position. For that, closed loop motion planning is done. As we grab the object, the degree of freedom of the robot is reduced from its actual 12 to 6. So for that other unactuated arm, we need to get the parameter, we need to perform inverse kinematics to get parameter of an actual arm, and for after that inverse dynamics has been performed. Here and the top left shows the trees generated using RRT star, and bottom left represents the path that needs to be followed for by end effector to avoid the collision with obstacle. The left side one in the figure, left side represent for path for the left arm, and the right side are represent for the right arm. After that, we simulate it on approach phase. Here in approach phase, we can see that the both arm is following different trajectory to reach that object that keep in front of that box. After approach phase, we need to manipulate this box from the in front of it to the top of the robot. Here, for that, closed loop dynamics has closed loop motion planning is done. Here the results of inverse dynamics has been shown. The torque in approach phase, we have 12 degree of motion, so 12 degree of freedom. So we got the torque plot for each and individual joint. Here cubical polynomial segments are used in between segments to get interpolate the value which, from initial to final position through intermediate position. And on the right hand side, there is only 6 degree of freedom. After grabbing the object, we have only 6 degree of freedom. So the 6 joint torque has been shown. Here cycloidal trajectory is applied from moving the object from in front of the robots to the top of the robot, its goal position. So in the conclusion, the strategy we have used to generate the path is working finely, and dynamic analysis is also done for open loop as well as closed loop configuration. That's it from my side. Thank you very much for giving me an opportunity.
Thank you for your presentation. Now, there are a few questions. The first is that how are you modeling collisions?
And for collision check, we have taken a sphere as a collision, and we assume the robot link as a cylinder and obstacle as a sphere. And after that, collision has been checked by using calculating the distance between the cylinder and the sphere center. If that sphere center and distance between cylinder and the center of sphere is greater than the summation of radius, both that's the cylinder radius plus sphere radius, then there is no we can say that it's not going to collide. If the radius is less than that, sum is less than the distance is less than the sum of the radiuses, then we can say that it's going to collide with the obstacle.
Okay, that was one. The other is since you're having 12 degree of freedom,
Yes,
there are infinite solutions. So how are you choosing the solution?
Sorry, sir, I didn't get the question. For
because you're having two arms, 6 degrees, 6 degrees, right?
Yes, sir.
So total system is 12 degree of freedom.
Yes, sir.
So it means that you will have infinite solutions to inverse kinematics.
Yeah, for closed loop, we have performed inverse kinematics. Yes, for that we have to perform forward we know the forward first position. Here, so for open loop configuration, we are performing directly forward kinematics case. But for open closed loop configuration, we know the position as the object place is object where to its need to move is already defined. So we know the initial position. So from that we have a 6 degree of freedom that we actuated. So for only left arm, we need to perform inverse kinematics as an actuated arm.
No, but even to go to that sphere, you can go in many ways, right?
Yes, we take the first solution as an inverse kinematic solution.
So what is the first solution?
That analytical equations has been shown in that paper, sir. I didn't add it here.
Okay. Thank you. Thank you for your presentation.
Thank you, sir.
Yeah. So the next paper is number 77 by Piyush Taylor, mono-camera-based localization of objects to guide real-time grasp of a robotic manipulator.
Yeah, hello. Am I like my screen is visible, right?
Yeah.
Okay. Good afternoon, everyone. My name is Piyush, and I'm a working professional in the field of robotics. And my research paper title is mono-camera-based localization for the objects to guide real-time grasp of a robotic manipulator. So, although we already know that through robotization has grown a lot in recent years, there has been a work which are related to which are simple, which are stable, as well as which need to be repeated from day-to-day life. So, for that we are replacing machines from we are replacing humans in the form of machines. So my work involves a real-time procedure for such an example. In the work which I have done, the process of sorting is done, which is based on color. Although it can be based on any other size, any other metric parameter also. And for the picking and placing of the object which is placed in the workspace, I have used a 6 degree of robotic system. So for literature review, like precision is one of the most basic thing and necessity for a robotic arm to function, because you might go with various inverse kinematics functions for optimized results, but however precision for using which are closed loop, so that if any position is missed or velocity is lacking, so that is one of the main challenge which we face when we are working with robotic manipulators. In my research-oriented paper, I have what has been done is based on the moving of the object, like moving people in the frame, which can be detected by the by any movement inside the frame, as it has been referenced in the Prof. C and Poggio paper, a trainable system for object detection. This, on the contrary, a novel probabilistic method of finding people is also being I have been going through for giving out best results, which is based on color, and the reference can be made from IOFA and Foresight from the paper probabilistic method of finding people. So the approach which I have followed is basically finding the workspace. So if it tends to begin that the camera has been dislocated or there's a problem with the workspace which we need to function on, so that is something which first my system clarifies. After that, it locates the object which is placed in the workspace, and a sorting process has been through the frames of the camera, which is based on RGB colors, and thereafter coordinates of the object has been given to the robotic actuator, so that it goes to the position and grab it, and this process has been repeated until and unless all the object has been cleared from the workspace. And it also functions in a dynamic environment if there is the addition of new objects which need to be sorted. So that can be also be like future work can be involved, like when the conveyor is moving and you have to sort out the colored object. So, in order to achieve that, I have used a series of sensors and actuators. My system has been divided into two parts, which is one is for vision sensing and the other one is for my camera. Other is for my mechanical actuator. So what my vision sensor does is that it takes a frame from the camera of the workspace. It then converts the whole system into HSV format, as HSV gives better results than RGB. And then a series of algorithms has been put through, which first detect red, which then detects green and blue. If any one of them is clarified, then it will give the location through PLC to the robotic manipulator. The robotic manipulator go to the required coordinates and put its end effector as to get to the location, and thereafter a gripper has been actuated through PLC only via Arduino, and these all things are needed to grab the object, and then it has been placed into the required bin. So for this, I have taken 3 bins as I am sorting 3 colors, and the process tends to also gives a GUI representation from Arduino, which gives that the gripper is working accurately or not, and another GUI has been done for that, so that if there is a change in size of the object, then that can also be monitored using the as the Arduino also uses current sensor, so that the GUI also represent how much current a motor is drawing, which can be mapped with the fact that what weight does the object has, or what size the object has to a particular extent. For this, performance of the robotic system was assessed in real time over various representatives 2D location of the object. The system started installation of robotic arm, and thereafter the computer system gets ready for the object visualization and localization. Suppose if there is no object present, the robotic arm will be at his home position, and they will wait for the command from the vision system. So a robotic arm moves towards the object via camera frames, coordinates, and the gripper picks up, which has been integrated. PLC has been a major integration from my PC to the robotic controller, as well as to the gripper controller, which is Arduino. So here's a frame which I have captured through my camera, and this has been sorting for the color, for the red color. As you can see, I am not taking the whole red color to the to my casting window. I have taken contours concept, which only takes the boundaries instead of taking the whole, so that it covers the major area. The initial challenges which I faced initially was, if suppose 2 objects are too close, then it will form 1 contour instead of 2. So that has been sorted out with the using by changing the light directions as well as megapixels of the camera. The table shows a representation of the actual value which has been put into the XY plane of my workspace, as well as the position which I get from my vision system. And the error has been minimized and optimized by changing up the direction and positioning my camera at particular height. The discussion and conclusion includes the novelty of taking embedded microcontroller, as well as monitoring the work process of the whole system, as well as the technique reduces the case of error of position of an object, which can be in case of, if suppose 2 objects are placed too fine, then there might be a collision with the gripper of the robotic arm to the other object, which is not to be picked at that moment. So that this all was in a real dynamic environment, and it tends to update it for the performance enhancement. After going through a series of trials, I have found that satisfactory level of repeatability has been achieved in robotic grasp and ungrasped operation for all the colored objects in the succession. Thank you. If you have any questions.
Yeah, so thank you for your talk. Now, these objects that you are grasping, they are normal 3D objects, or they are regular 2D objects?
So they are 3D objects.
So it can be any object, like a
it can be
a cup or anything.
Yeah, no, sir. There is limitations for, like, my gripper has limitation of the opening, so it cannot be larger than the opening of my gripper.
Okay, but you don't plan the grasp, right?
I don't plan the grasp. Yes, sir, I do plan the grasp when the object, when like I have, when the my robot and effector go to a particular position, then it tends to open the gripper first, and then it will go deep in the plane to grab the object. So I command it indirectly.
Okay.
Yes,
okay.
sir.
Thank you. Thank you for your presentation. So
Thank you so much.
The next author is Aditi Deshpande, reference frame for coordinating robots for movement of objects.
Is it visible?
Yeah, it's clear, yes.
So, good afternoon.
Please start.
I am Aditi Deshpande. I did my BTech from PES University. So, our project is a reference framework for coordinating robots for movement of objects. So, movement of objects in factories and other industries is a tedious task, and having robots to perform these tasks increases the productivity and also decreases the burden on humans. The automation becomes even more important for hazardous environments such as environments with high temperature variation or radiation, and areas with harmful chemicals. So, this framework is developed for such applications in which multiple robots work to accomplish the payload movements. So, various algorithms such as pattern search algorithm, genetic algorithm, particle swarm optimization were used in the path optimization. And among these algorithms, pattern search algorithm was found to be the most feasible for a workspace of any area. And also the robots took the least amount of time for the pattern search algorithm. Coming to the detection of objects, detecting objects based on shape, color, deep learning using TensorFlow were explored, but all of these had their drawbacks as it was either dependent on light intensity or they inaccurately detected the object. So object tracking using OpenCV was implemented. So CSRT tracker was found to be the most accurate for tracking the moving objects in real time. So this framework works well with dynamically changing obstacles and with other moving robots or agents in the environment, and it is also self-governing in terms of robot movements. And pattern search algorithm was implemented on a hardware and was proved to be very efficient in a practical environment. System setup. So the setup as shown in the figure has 3 robots which pick the payload and maneuver around the obstacle to reach the target, which is shown as a cross mark. And also there is a master computer to which a web camera is attached. So the robots in the workspace is detected using a web camera based central system, and there is a path optimized for each one of these robots, and this is done using a pattern search algorithm. So in this, each coordinate is taken and 8 points around this coordinate is chosen, and the objective function value for each one of these 8 coordinates is calculated. And based on this, the least value is taken, which determines what step the robot should take next. So and also each worker robot is assigned with a unique identifier. So the communication model encodes the data in a form of 9-byte string, and the worker robot receives this, which has a transceiver attached, and it decodes the message and sends back the acknowledgement to the master that it has received and takes the desired action. The hardware setup consists of the worker robot is shown on the left side, which has the Arduino, a transceiver, motor drivers, batteries, and it also has a gripper to hold the objects. And the right side shows the robots in action, where the white blocks are the objects to be picked, and the red blocks indicate the obstacles, and the circle is the target. So So methodology, so the robot, the control is with the master, and there are two subsystems, vision subsystem and motion subsystem. So the vision subsystem has is where there is a web camera attached to the master, and the robot position coordinates are determined, and it is passed to the CSRT tracker where the tracking happens in real time. And the motion subsystem involves the path optimization where coordinates of each step that the robot has to take is determined, and also the orientation and the angle of the robot is found, and this is communicated to each robot which move in the required path. So results, a typical optimized path is shown in the first diagram. So the robots must avoid the red obstacles, pick the blue squares, which are the objects, and move to the target. So until the payload is picked, the objective function is calculated with respect to the payload. And at the just when it is picked, the objective function is 0, which is shown in the graph. And after the payload is picked, the objective function is calculated with respect to the target. That is the sudden change in the sudden spike that is seen in the graph when the object is picked. And after that, once it's calculated with respect to the target, the objective function goes on decreasing and ultimately becomes 0, which indicates that the target has been reached. So this trend was found to be the same when we did this for different environments and placed the objects and obstacles at different places in the workspace. So conclusion, so this is a framework where 3 robots were used, and they had to pick up the payload, maneuver around the obstacles, and move to the target. And this can be extended to multiple robots for performing tasks as team members and interacting with each other and also coordinate the actions that benefits the whole swarm. And it works well with dynamically changing environment, that is when the obstacles are moving as well. And since each robot is equipped with a radio transceiver, they're also capable of communicating with other robots and with the master, thereby increasing the levels of communication to transmit the information for a collective and optimal action by the swarm. So this is the future.
Okay, thank you for your presentation. The question here is, when you're saying this is the optimal path, so in what way are they optimal?
It finds the shortest distance, and also it moves in the least amount of least time, duration of time. This way it is optimal.
Because shortest distance is a straight line.
Shortest distance depending on the environment, based on the obstacles and other robots are in the path. So based on that, sir.
Okay, so it dynamically changes its path also, or it is not dynamic?
Yeah, as it moves to the next step, it again calculates the finds the value of the objective function based on the situation at that point of time, and takes the best step at that point of time.
Okay. Okay. Thank you.
Thank you, sir.
Thank you. So the next paper is by Ravikant Jain, Development of IoT-based inspection robotic system and controlled using web Android application.
Good evening, sir.
Yeah, please start.
This paper focus on the development of IoT-based inspections robotic system controlled using the web applications, web/Android applications. We are from CSR CMERI, along with Dr. Deep Narayan is the one of the co-author of this paper also. And the motivation of this paper behind it, most of the mobile robots are commercially available in the military, medical, agriculture, domestic, and other industrial also. Industrial where major task is the inspection is the major task, which is a very difficult task to monitor actually. So considering this aspect, computer controlled robots are available, most of the researchers are working. But where we are introducing the IoT based concept, IoT means Internet of Things, which can provide the intelligence device to monitor the event happening around them by making the local and distributed intelligence to decide the course of action and then manipulate the object in the real-time applications. So this is provide the new generation of the robots for performing the autonomously. Where we can one major advantage of this, we can sensor data, we can store the sensor data, and this data can utilize for the big data analytics purpose. So this is the one way possible for remotely visualize, monitoring, analyze, and optimize the control of the inspections report. So going the background as well as the literature survey, from 2000 onwards, inspection task is banned by the human deployment, banned by the government of India. So there, what happens inside the pipelines, damage happening. So how we can monitor without deploying the humans. So Japan has done some work regarding this inspections robot. They have deployed one field robot, and some Malaysian university technology means a concept on the pipeline inspections robot, as well as the Bata University from the Czech Republic has on the one small robots for the sewage line. And this some students from the Bangalore, Dr. Ambedkar Institute of Technology, Bangalore, they have explored this concept of the pipeline inspection as well as the cleaning robots actually. And then some military university, they explored this drainage cleaning robot by using the some pressure systems actually. And recently, one drainage mapping robots has been done by the Singapore University. So considering this backgrounds, we have also proposed objective of this proposal, design development of the IoT-based drainage inspections robot, which can be used for the monitoring inspection of the drain, tunnel, and sewage pipe. Where major objective considering the unstructured environment. So we have proposed the 6-wheel robot system for the unstructured environment. Inspections of the inner surfaces damage of the tunnel. For the health of the pipeline, provide the visual surveillance like crack, leaks, and other mechanical damage can be identified. Where we are applying the IoT technique for the online monitoring and inspections. After applying this IoT technique, this process data we can store in the cloud environment for developing the analytics. How is robot's behavior? And this remotely controlled is the continuous monitored data over the ground we are taking using the web Android applications, means it can also control through the mobile phones. So concept is this robots. We have considered the drain size is the 550 mm width, and height is the 750, and we have put the one cutter also and suction systems also along with the camera systems, and these are the features has been identified after simulating environment in the ADAM simulations. Robot parameters has been identified. Total weight we have considered the 58. Velocity is the 200 mm per second. Wheel acceleration is the 4.75 accelerations. Total power consumption is required for the movements is the one round is the 150 watts. So prototype we have developed. One prototype we have developed where we system architectures of the control system, identify the motor controls as well as the visualizations of the system, and considering that these suction systems also used. And after that we have this system architecture for the IoT systems. We identify the node MCU where we have used for the wireless communications applications, and we have one mobile app we have developed through this robot control through the mobile app, where we can log in by the authentications on self, and we can control the robot by left, right, or movements of each robots. And after that, this data we have uploaded in the cloud computing, cloud environments, in the think speech environments. And then we are monitoring how it is showing the behavior inside the tunnel, and we have demonstrated this robot in our CSR CMRI colonies. And after that, this data can be stored or sent to the other applications. So, a conclusion of this paper: web-based applications of the mobile robot using the IoT platform is discussed here. And system architecture is designed for the monitoring, control of the robot positioning, and monitoring of the drainage tunnels. Mobile robot interface with the microcontroller and node MCU through the wireless communication with the cloud network systems. And this network system major advantage is store the data and continuously and access the remotely through the web applications. This kind of web application demonstration shows the Android applications can be also used for this kind of robotic application, mobile robotic applications, and this is providing the new generation of the robotic systems, and this provide the good solutions for the monitoring in the industrial coal mines also, and pipeline and tunnel where deploy of the human is very difficult. Thank you, sir.
Yeah, thank you, Ravikant Jain, for your presentation.
Yes, sir.
Yeah, a few questions are there. First is that this is expected to go in underground pipelines and tunnels and places like
Yes,
that.
sir.
So,
Yeah.
so any special design in terms of traction or wheels that is being implemented?
Sir, here we are using the hard wheels because soft wheel will not go inside there. So one is the major advantage this. Another is the wireless communications environment. So when you are going the coal mine or tunnels, then first we have to connect the signal wired communication to the wireless communications, and then by installing the different routers, then we can control our signal from the robot section. As well as our CCTV camera based systems means camera used. So this also can provide the good quality of the tunnel means underground.
Okay. Okay. Thank you. Thank you for your presentation.
Thank you, sir.
So the next speaker is Deep Narayan Ray. Is he there?
Sir, good afternoon.
Yeah, good afternoon. So your title of your talk is Design and Comparative Study of Mechanisms for Variable Ground Clearance for an Unmanned Ground Vehicle.
Yes, sir.
Yeah, so please start.
Sir, basically, this is a work where in the upcoming days, the domain of UGV is being enriched. Basically, as per the latest market trend, the UGV is coming up as a next robot, which can be used both for military as well as commercial application of for various hazardous and dangerous and monotonous tasks. With this, we started a work, and this is a joint work with DRDO. So the first problem was that we have a problem with the ground clearance. Basically, the UGVs I have most of the time either have to move on flat road, flat or plain land, and sometimes or most of the times it has to move over very rough terrains. So when it is moving on very rough terrains, the ground clearance should be preferably high, so that it can easily cross, or it can easily pass over the largest obstacles, or whatever obstacles comes in its path. But but its ground clearance should be higher, on the higher side. If the obstacle is it can be easily crossed, or easily can be overcome. Otherwise, if the system is running on the flat terrain, it should move on very high speed to reach from point A to point B, and that time to maintain a stability, the ground clearance should be lower one. So with this intuition in our mind that when the system is moving on flat road or plain land, we can keep the ground clearance as minimum as possible, and whenever it is moving on rough terrain with a lower speed, we can increase the ground clearance. And these type of activities, means this type of feature is already being incorporated in various cars, mostly by this Mercedes, and the most common one is Bosch. They have Bosch. They have already used this MR fluid based actuation system to get the disturbance before the vehicle passes over it, and accordingly the suspension system takes care of it. So in that sense, they maintain the ground clearance as well as suspension. But here, a number of work we have found where people are either using pneumatic, the first one, concept one, they are using a pneumatic system so that just on the left side, these blue elliptical ovals, they are showing that the top one is the initial position and the bottom one is that there is a red expansion of the actuator so that the platform can be raised so as to increase the ground clearance. So this is one concept where pneumatic cylinders and air has been used. And another one is this concept two, where hydraulic cylinder is used to increase the height and obviously the ground clearance. And third one is with some gear-based mechanical arrangement which required regular maintenance and obviously other activities, means to check the vibration for other sensors mounted on it has to be taken care of. And with this, basically, this was our target vehicle, ground vehicle, where we have found some articulated arms articulated arms have been used, but they never use this type of concept. Basically, this is also geared mounted arm which can rotate along the center pivotal point, and the ground clearance can be increased. But we have a design of a vehicle which is capable of carrying a payload of 100 kg, but the vehicle weight must be within 200 kg. And most of the time, this was the initial attempt. Why 100 mm? Why not 200 mm? So initially we kept it a minimum. That what is the minimum height it can raise? So accordingly, a number of actuators have been identified. So this is the methodology how we have achieved the basically it is a comparative study. We have studied the mechanism available for various UGVs for this type of ground adjustable ground clearance, and thereafter we find out what are the components and their functionalities, and how they can be maintained regularly or without maintenance, how they can run. And obviously the most one is the simplicity of the system, ease of operation. So basic on the basis of these components and this type of actuators, we have referred to the standard catalogs available with those particular manufacturers. Say for pneumatic, there is SMC is there. For electrical actuator, we have also referred to some catalogs. And similarly for hydraulic, we have also tried to develop the system at a local basis. But this is very humble submission that due to this pandemic situation and several lockdowns, so though we got the hydraulic system, but pneumatic and electrical actuator we didn't receive at our lab due to these conditions, and though they were pending, but till date we haven't received. So the experimental validation cannot be done. But this comparative study gives us an overview. Basically, we need to achieve the 100 mm ground clearance. But sometimes if we need in between 0 to 100, so that is also required. Say if I need to make the ground clearance 80 mm, then the previous one. Obviously, this 100 mm means from the if initial it is 80 mm, then the final ground clearance should be 80 plus 100 mm. This 100 mm is that the additional one in terms of this relative initial value. So with this, a number of studies, basically parametric studies and their use of operation, their circuitaries have been studied. How many components are there, And all of us know that pneumatic and hydraulic, they, apart from this hydraulic cylinder or pneumatic cylinder, we have to use this either air or oil, hydraulic oil, and this hydraulic oil should be filtered, and there should be definite control mechanism to pass the fluid for obtaining different movement of the actuator, and obviously accumulator, pressure gauge, everything is there. So in a sense, when we formulated the circuit of such a hydraulic cylinder, we found that it's a very complicated one. But whenever the UGV in operation on a remote field, and you need to increase the ground clearance or decrease the ground clearance for moving away from the position, so it is very difficult. Means the response time is very means it is, I am telling it theoretically, so it is very lower. The response time is higher than that of our electrical actuator. And these are
Deep, your time is almost up.
Yeah, with this theoretical study between the pneumatic circuit and hydraulic circuit and linear actuator, we with these specification values of the vehicle, we made up this study, and thereafter we find out that electrical actuation system use only the actuator and its control. Basically, from the vehicle control, it's move faster. So with this, we did up a schematic test setup. This setup is already ready for hydraulic system, but due to non-availability of other two, I cannot complete the experiments. And as I showed you that with the linear actuator, electrical actuator, we made some simulation for such a UGV. It's a 6x6 vehicle, and obviously we have also tested the various suspension system designed for this. So during this was the initial condition when the ground clearance is around 250 mm, and the actuator is working as a steep or fixed rod. So with this means this has helped us to simulate the working of the UGV, but experimentally till now, due to unavailability, we cannot complete the full work. So with this, I end up my presentation here.
Okay, thank you, Deep. So the output of your study is that essentially you are suggesting that you should have electrical linear actuator.
Yes, sir.
Okay, thank you. So the next presenter is Sudhanshu Ranjan, development of modular library of rapid prototyping of planar hybrid linkages using computer-aided design.
Good evening, sir. I'll be presenting my screen.
Yeah, can you speak a little bit louder or bring your microphone closer to your mouth? Not much.
Not much. Okay, I'll try.
Maybe you can turn off your video feed if you want.
Yeah, turn off your video.
Good evening, everyone. I'll be presenting my work on the topic. I'm a student, BTech and MTech dual degree, Indian Institute of Technology, Robotics, and I'll be presenting on the topic development of modular library for rapid prototyping of planar hybrid linkages using computer-aided design. So one of the major challenges in prototyping hybrid linkages has always been that the design process of every linkage has to be unique and done from scratch. And having a modular library where components can be directly incorporated in the model design assembly and thus enable prototyping of whole non-assembly linkages in one go, would extremely reduce complexity of the process as well as the time taken. So works have been reported in the past where to study the kinematic and dynamic properties of linkages, all of the prototypes have to be modeled from scratch, and various theoretical works uh, have also been reported which use simple modules to analyze and predict properties of different hybrid linkages as shown in the figures here. And therefore integration of a modular approach in design of a rapid a fairly novel idea, and which is explored in this work. So our problem statement therefore becomes that given a planar mechanism with predetermined link attributes, can we design a modular library elements to prototype the given configuration? And therefore our objectives become, to design a modular library having elements to be assembled and then prototype a hybrid linkage, as well as to suggest a methodology for selection of printing parameters, and which is suggesting an algorithm for the usage of the designed library. So for the first part, the selection of printing parameters, the layering plane has to be same as the plane of motion, and ensuring lowest time of prototyping as well as maximum strength. A lot of research is available for selection of optimized clearances for different kinds of joints, especially for revolute joints. No scaling is required for the clearances since the joint design is fairly simple, and we have limited it to the revolute joints. However, scaling might be required for the complete assembly upon final design to fit the printer build volume. So this can be achieved by using inbuilt scaling tools available with most CAD platforms and edit the clearances. Several modules have been designed to implement the modular functionalities like the active joint, which is achieved by fixing the control to the active pin and attaching a gear transmission, which can be used to attach with an actuator and maybe and then control the motion of the controlled link. Passive joint and joint locking modules have also been designed so that we don't need to lock the joint at a certain position actively by attaching an actuator. Connectivity module is designed to add the functionality of being able to connect two or more simple modular linkages axially and thus form hybrid ones. Implicit FEA analysis was done for the tensile load on the pin joint, since tensile loading is the most critical kind of loading for the pin joint here. As the layering plane is in the plane of motion itself, and we know that printing these modules would lead to minimum strength in the perpendicular direction. And using an anisotropic model for FDM printed ABS material, and according to the analysis, according to the analysis, up to 5 megapascals of tensile load is understood to be safe. As a result, we have the algorithm for the modular library to be used to produce models of hybrid linkages ready methods. And we take the input parameters and importing the relevant modules one by one for every joint. We finally obtain the output, which is the CAD model for the hybrid linkage that is required to be prototyped. These prototypes can be then printed using AM methods such as FDM as a cheap choice, or SLS as an expensive choice. The implementation of the algorithm has been done to produce models for various hybrid linkages developed by co-author Sakshi Gupta in a separate work for which he did for assisting human limb motion rehabilitation using exoskeletons. So we have the final linkages here, which have been produced using the designed modular library, and therefore the objective of providing a platform for CAD design of for prototyping has therefore been accomplished, and has been shown by producing such models using the design library. These models can be directly printed using AM techniques And the idea of introducing modularity in design for rapid prototyping is fairly new, and therefore the research appears to be quite novel. And thank you, sir. That will be all.
Yeah, thank you for your presentation. The question here is, if you have multiple solutions, for example, you could make a 4-bar mechanism using different linkages, right? Is there a smart way of saying which is the best mechanism in some way?
So here we have just implemented taken those at input parameters. Like the designer has to be ready with a modular linkage, and then they just have to prototype, and we have built a modular library to implement that.
Okay, so the designer gives you the final product, and you just take the parts and put it together.
Okay. No, sir. Actually, if the if the problem is in prototyping, sometimes we don't have we have to build the whole model from scratch, and then we can prototype. But if the designer has a given modular linkage, then we have provided a library. So these elements they can import directly and then form their linkage, and they can print that directly. So
yeah, so that I understood. My question is, suppose it is possible to do it in 2 ways.
Yes, sir.
In that case, is there some smart way of choosing which part will come?
No, sir, we have not implemented that. We have given priority to customizability, which is giving a choice to that any kind of module can be actually built.
Okay, thank you.
Thank you, sir.
Okay, thank you. So the next speaker is Naka Sanjeevi, lower limb muscle force analysis for a knee joint intervention strategy.
Yes, I'm sharing my screen.
Yeah.
Yeah. Is my presentation visible?
Yeah.
Yeah. So good evening, everyone. So I am Sanjeevi, a research scholar at Human Centered Robotics Lab, IIT Gandhinagar. So today I'm presenting the work titled Lower Limb Muscle Force Analysis for a Knee Joint Intervention Strategy. So to begin with, as we all know, like walking is a main form of locomotion in humans, and it helps us in accomplishing many of our day-to-day activities. However, with the onset of neurological disorders such as stroke, spinal cord injury, or cerebral palsy, affects the walking pattern in humans. So the affected individuals typically tend to show a gait asymmetry, improper balance in walking, decreased range of motion, loss of weight-bearing capacity in the affected leg, and on. So, to improve the functional walking, one way is conventional approach is to go to the therapist, where the subject will be made to walk on a treadmill, undergo repetitive walking motion. And another way is, over the past couple of decades, another technique is use of with the development of robotics technology. Various leg exoskeletons have been developed for rehabilitation purpose, where they give a repeated control to motion training, and it helps us in better quantification of motor recovery, gives us much better feedback through the use of various sensors, and also reduce labor needs. However, of late, there is further, with the increase in the understanding of the human biomechanics, there is increased interest in understanding the effects of single joint force intervention strategies for lower limb rehabilitation applications. As you can see, our human lower limb, human body by itself is so much redundantly actuated. It has so many muscles in it. So human musculoskeletal the lower limb musculoskeletal structure I have shown here, you can clearly see the number of muscles that we have to achieve the certain amount of degrees of freedom in task space. Now, here what is the interest is, so we have a couple of biarticular muscles, single uniarticular muscles, where like biarticular muscles, actuating that particular muscle creates actuation at multiple joints. So this redundancy and the existence of such muscles has gathered attention wide. Where is there any way, if we intervene at a particular joint, can we improve, can we affect other joints, etc. So there is increased interest in developing such rehab strategies. Whereas while designing such rehab paradigms, it's always necessary to know when to intervene, the timing of the intervention and the level of force intervention to prevent activation of undesired muscle groups. And again, why this is because we have so much redundancy, and we may tend to start using activate some other muscle groups to achieve the motion. So this is where musculoskeletal dynamic models and simulation analysis benefits. It helps us in deciding these intervention strategies. We can simulate various environments in the modeling softwares. We can go through certain set of results, and we can conclude whether to go with which set of design, etc. So accordingly, in this work, we attempted to study a knee joint intervention strategy by adding an external spring element at knee joint, and we tried to study how it affects muscle activation patterns, thus to try to deduce how it affects hip joint and knee joint variations. So the methodology is like we used OpenSim. It's an open source musculoskeletal modeling software for the analysis. There are a couple of lower limb models that are available, full body models, lower limb models, etc. In this, since we are targeting knee joint intervention, so we choose a lower limb model, and in that we use a 10^18 muscle model, which has 10 degrees of freedom and 9 muscles on each lower limb. And among those 9 muscles, we choose only 5 muscles for the analysis, which are primarily needed for knee joint activation and hip joint activation. And further, we analyzed the muscle force pattern across one full gait cycle for different spring length combinations. So the 5 muscles that we used are hamstrings, gluteus maximus, vastus intermedius, rectus femoris, and gastrocnemius. So which are needed for hip joint activation, hip joint flexion extension, knee joint flexion extension, etc. So now the 2 conditions that we studied that we analyzed in this study are like positioning this passive spring on the posterior side of the knee joint and on the anterior side of the knee joint. And we used different spring length combinations to see how it affects the muscle activation patterns. And we, at a constant spring stiffness value, we analyzed this study. And we position the spring, initial and endpoints of the spring are positioned at the centroid of the tibia and centroid of the shank, femur, sorry. So now if you look at the simulation pipeline, so OpenSim has a lower, so we can scale the model with the subject's anthropometric parameters, and we used a MATLAB application interface to add an external element. So here in this particular case, we added a spring. However, it facilitates us to add damping elements or external mass elements also. So using this interfacing, we added a spring element. To the updated model, we had defined the desired spring length. And using this updated OpenSim model, let me use updated OpenSim, we re-simulated the full body motion, and we come up with, so what OpenSim does is it solves for the muscle activation forces with the new environment that we have simulated. It gives us a new set of muscle activation forces which are required to achieve the same motion with the external resistance element in the environment. And we used that muscle forces and time series plots to analyze. So now this is one such result that I'm presenting here, where this, as I have mentioned, we used 5 muscles in the study, and this table highlights their contribution to the gait. So hamstring assists for hip joint extension and knee joint flexion. So this is a biarticular muscle. So gluteus maximus, vastus intermedius, and gastrocnemius are primarily affects gluteus maximus affects hip joint, and vastus intermedius and gastrocnemius affects knee joint, and rectus femoris is again a biarticular muscle. Now, if you see the blue curves in all the 5 graphs show the baseline muscle activation patterns, where once we add springs, you can see a clear variation. So let's look at vastus intermedius. So vastus intermediate muscle is responsible for knee joint extension. Now, here what this particular set of result is for attaching spring on posterior side. That means I'm assisting my knee flexion. So if I'm assisting knee flexion, essentially means I'm creating a certain resistance to extend my knee, because the spring try to resist the knee extension. So now to achieve the gait motion, my vastus intermedius muscle, which is responsible for knee extension, has to do more and has to produce more muscle force to achieve the motion. Similarly, we have dip in gastrocnemius. As I'm assisting knee joint flexion we have observed deep in the gastrocnemius muscle. However, you can also see that there is a change in muscle activation patterns for hamstring muscle and rectus femoris, which are biarticular. Biarticular by means, so of course it's affecting my knee joint activation. At the same time, it will bring some changes in my hip joint also. So these kind of analysis one can do to get an understanding of how human muscle activation patterns changes with intervening at single joint. So another such analysis is providing knee flexion resistance, that is positioning spring on my flexion side, on the post anterior side. And again, we have observed similar such results where we have seen changes in the biarticular muscles, thus affecting that, which might affect my hip joint also. So key observations that we made in this study are muscle patterns, of course, have varied significantly by varying the spring length. However, single joint intervention may bring changes across multiple joints because due to the existence of joint coupling by biarticular muscles, and altering these muscle activation patterns may trigger compensatory strategies, which needs further more detailed lab-based studies also to provide much further strong base. So overall, to conclude, we presented the potential of musculoskeletal dynamic models and simulation analysis in deciding some intervention strategies. We observed that applying resistive forces alter muscle activation patterns. However, the one thing we envision from this is like we can model various environments in the OpenSim. We can come up with several design parameters like what should be my spring stiffness, what should be my spring length, or if I'm using any external element like damper, to know we can get to know about their damping parameters. So such analysis benefits us in specific rehabilitation devices. Like one such in the figure where I have shown a passive exosuit having, we can envision such devices where like we can have fabric kind of fabric braces, and we elastic elements stitched within it, which kind of provides some assistance or resistance during one particular part of my gait phase, depending on its initial length conditions. So such these kind of benefit, these are like home-based rehabilitation. So all these are like this software offers. So we try to bring out that potential thought process. Yeah. So that's all. If you have any questions.
Okay, thank you for your presentation. So what I understood is that you're trying to position the damper in the posterior side or the front side.
So here in this one we use spring, not the damper. But I'm telling.
Yeah. So my question is that don't you need a damper also, because only a spring will lead to some kind of vibration and.
If you further evolve, yeah, we try to show some preliminary results, like we just added a resistive element and see how it affects multiple joints, whether we can see changes in muscle patterns of biarticular muscles, how it may affect other joints, to get an understanding.
Okay, that is one. That in terms of spring, one problem with the spring is that it tends to vibrate. The other is that you are doing only half cycle gait. Our leg.
No, we have presented. I present for full cycle. Yeah, from heel strike to heel strike of right leg.
Of
right leg, heel strike to right leg is one full gait cycle. Yeah.
Yeah. So that will mean that your spring stiffness, because when it is supporting when the foot is on the ground, it is supporting the full body weight.
Yes.
But when it is on air, it's not supporting anything.
Yeah.
So
So
the
that
stiffness does vary.
True. So so what we did is that's what I'm trying to tell. So these analysis will benefit us in deciding even the spring length. So spring stiffness is one thing, and the length of spring is another thing. So let's say if I increase the length, if my leg is fully extended, and if spring applies some force during that part, and as soon as I start bending my knee, like flexing my knee, it tries to assist my knee flexion. Or if I use much lengthier spring, it might not do that, right? So we use these design parameters with these kind of studies.
Yeah. So what I'm trying to say is that you actually need an adaptive kind of a system there, adaptive K or adaptive damping also. That's what happens in the human leg. Like when we are running or walking or jumping, we tend to change our stiffness as required.
Yes.
And that is a real challenge, how to design a mechanical system which can do that.
Yeah.
Okay. Okay, thank you for your presentation. So I think we are done with this session, right?
Yes, sir.
Okay. So 5:35, not bad. Okay, so hopefully they have, people have gone and they're at the table.
No. We'll have to exit now. Then only we'll all
Oh,
go
yeah,
there.
yeah, we have to exit, yes. Okay, so let me make the announcement. So, okay, thank you for attending today's session. So we have concluded the last session today. Tomorrow morning, we start at 9 a.m. The plenary speaker is Professor Seol Jung from Chungnam University, National University, Korea, South Korea. And he'll be talking about balance in mechanisms and in life. So please do attend the session from 9 a.m. and listen to the plenary speaker talk about balance in mechanisms and life. After that, we have session number
7 on posters.
Poster session number 7, and in which we also have an industry talk. So there is an interesting industry talk from Dr. Jagannath Raju of Systemantics. So they are a robotics company which has been making industrial robots from scratch in India. So he has a talk from 10:30 to 11, which will be followed further by session number 8, which is on biomimetic and computer vision. After lunch, we have one session. Then we have another plenary talk by Piyush Menon, who is the Deputy Director of Autonomous Systems Lab in University of Exeter. And he'll be talking about mapping ocean. And after that, finally, we have the closing ceremony. So tomorrow is the last day, so make the most of it. Please come at 9 o'clock and listen to the interesting talks. Okay, thank you.
Okay, we'll all go to the networking area once we click on a button. So all the posters presenters, please go to your respective poster, double click on that particular table, be seated. Other audience are requested to just walk around, go through the posters and interact with your other peer presenters.
Yeah, so the posters are there as per the poster numbers, right?
Yes.
Yeah.
The table have poster number. Kindly go to your respective table.
Yeah, and for the others, if you want to see any poster, then the paper number is given on the left side and the right side columns. If you click on that, you can see the respective poster. A PDF file will open and you can see what is written on the poster. And if you have questions, you can go to the table and then ask the author. Okay?
So this is an open-ended. We'll keep it open as long as it want. Like you can just hang out and interact, because so far we haven't had any networking sessions per se. So please stay around, interact with people.